What is the universe hiding from us? From the invisible dark matter holding galaxies together, to the black holes where physics itself breaks down, to the terrifying possibility that everything, space, time, even the Big Bang, could be part of something even stranger. Today, we're counting down the 50 greatest unsolved mysteries in cosmology. Some of these questions have puzzled scientists for a century. Others we've only just discovered. And the last one? It might be the biggest question anyone has ever asked. Let's dive in. 50. Why is the night sky dark? Olber's Paradox. Imagine stepping outside on a perfectly clear night. Above you stretches an ocean of stars, glittering across the darkness. Thousands are visible to the naked eye, and telescopes reveal billions more. Beyond our own galaxy lie hundreds of billions of other galaxies, each containing billions or even trillions of stars. By every measure, the universe is overflowing with light. So why is the night sky dark? At first glance, the question sounds almost childishly simple. But for centuries, it puzzled some of the greatest scientific minds. Today, it is known as Olber's Paradox, and its solution would become one of the first clues that our universe is far stranger than anyone had imagined. In the early 19th century, the German astronomer Heinrich Wilhelm Olbers popularized a fascinating argument. If the universe were infinite, eternal, and uniformly filled with stars, then every line of sight from Earth should eventually end on the surface of a star. Even if distant stars appeared dimmer, there would be infinitely many of them, and together they should flood the sky with light. Night should be as bright as the surface of the sun, but it isn't. For years, astronomers proposed explanations. Perhaps distant clouds of dust blocked the starlight. Yet this idea quickly fell apart. Over immense spans of time, that dust would absorb the radiation, heat up, and eventually glow just as brightly as the stars themselves. The darkness remained unexplained. The breakthrough arrived with a revolution in our understanding of the cosmos. The universe, scientists discovered, is not eternal. It had a beginning approximately 13.8 billion years ago. Because light travels at a finite speed, we can only receive light from stars whose rays have had enough time to reach us. Countless stars beyond this cosmic horizon remain invisible, their light still crossing the vastness of space. Even more remarkable, the universe is expanding. As galaxies race away from one another, the light they emit is stretched into longer wavelengths through a phenomenon known as redshift. Much of that ancient starlight is shifted beyond the range of visible light into infrared and microwave wavelengths, becoming invisible to human eyes. The darkness above us, then, is not empty. It is filled with ancient light that has been transformed by the expanding universe. What once seemed like a simple question about the night sky became one of the earliest pieces of evidence that the cosmos has a history, a beginning, an evolution, and perhaps an ultimate fate. Every patch of darkness is not an absence of light, but a reminder that we live in a universe still unfolding, where even the silence of the night carries the story of the Big Bang itself. 49. What is the shape of the universe? Picture yourself standing on a lonely mountaintop under a sky filled with stars. The horizon seems endless. Every direction looks the same. It feels as though space stretches forever in perfect straight lines. But what if that impression is an illusion? What if the universe itself is curved in a way our minds can barely comprehend? This is one of the greatest mysteries in cosmology. What is the true shape of the universe? At first, the question sounds simple. Yet its answer could determine whether the universe is infinite or finite, whether it will expand forever, and even whether traveling in one direction long enough could eventually bring you back to where you started. For thousands of years, geometry seemed absolute. Parallel lines never met, and the shortest distance between 2 points was always a straight line. But in the early 20th century, Albert Einstein's theory of general relativity transformed our understanding of space itself. Gravity was no longer viewed as an invisible force pulling objects together. Instead, massive objects bend the very fabric of space and time. If gravity can curve space locally around stars and galaxies, could the entire universe possess an overall curvature? Cosmologists describe three possibilities. The first is a closed universe, shaped somewhat like the surface of a sphere. Such a universe is finite, but has no edge. Travel far enough in one direction, and in principle, you could return to your starting point. The second is an open universe, with negative curvature resembling a saddle. In this geometry, parallel paths gradually diverge, and space extends endlessly with a distinctive curved structure. The third possibility is a flat universe. Here, the familiar rules of Euclidean geometry apply on the largest scales. Parallel lines remain parallel, and the angles of a giant triangle add up to exactly 180 degrees. So which universe do we inhabit? To find out, scientists have turned the cosmos itself into a laboratory. By studying the faint afterglow of the Big Bang, the cosmic microwave background, along with the distribution of galaxies across billions of light years, astronomers have measured the geometry of space with astonishing precision. The results consistently point toward a universe that is remarkably close to perfectly flat. But close is not the same as exactly. The tiniest margin of uncertainty leaves room for extraordinary possibilities. A universe that appears flat within our observable horizon could still curve on scales far beyond what we can ever see. It might be unimaginably vast or finite in ways forever hidden beyond the cosmic horizon. Every new observation sharpens the picture, yet the ultimate answer remains just beyond our reach. The shape of the universe is more than a question of geometry. It is a clue to the origin of everything, the destiny of the cosmos, and the limits of human knowledge. Somewhere in the silent curvature of space lies the blueprint of reality itself. 48. Is the universe infinite? Look up at the night sky. No matter how powerful our telescopes become, there is always something farther away, another galaxy, another cluster of galaxies, another horizon waiting to be explored. It raises one of the oldest and most profound questions humanity has ever asked. Does the universe go on forever, or does it have an end? At first, the answer seems obvious. If you traveled far enough in a straight line, surely you would eventually reach the edge of the universe. But modern cosmology tells a far stranger story. According to everything we've learned so far, the universe may have no edge at all. The first thing to understand is that the observable universe is not the entire universe. Because light travels at a finite speed, and the universe is about 13.8 billion years old, we can only see objects whose light has had time to reach us. This creates a cosmic horizon roughly 46.5 billion light years away in every direction. Beyond that boundary lies a vast region we simply cannot observe, not because it doesn't exist, but because its light has not yet arrived. So what lies beyond? One possibility is that space continues forever. An infinite universe would contain an endless number of galaxies, stars, and planets stretching into the unimaginable distance. Somewhere, unimaginably far away, there could even be regions almost identical to our own, perhaps even exact copies of Earth, created simply because every possible arrangement of matter would eventually repeat across infinite space. But infinity is not the only possibility. The universe could instead be finite but unbounded, much like the two-dimensional surface of a sphere. Imagine an ant walking across the Earth's surface. It would never encounter an edge, yet the surface itself is finite. In 3 dimensions, the universe might possess a similar geometry, allowing space to wrap around itself without any boundary. So how do scientists investigate something beyond our reach? Astronomers search for subtle clues in the cosmic microwave background, the ancient light left over from the Big Bang. If space were curved or wrapped around itself, Patterns in this primordial radiation might repeat across the sky like reflections in a hall of mirrors. So far, no convincing evidence has emerged. Every observation suggests that the universe is extraordinarily large and possibly infinite, but certainty remains elusive. And that is the heart of the mystery. An infinite universe challenges our intuition, our mathematics, and even our philosophy. A finite universe without edges is just as difficult to imagine. Perhaps the true answer lies forever beyond the observable horizon, hidden in regions we can never reach. As we peer deeper into the cosmos, one unsettling realization grows stronger. The universe may be far larger than our minds were ever meant to comprehend. Whether it stretches endlessly into eternity or curves back upon itself, its true size remains one of the greatest unanswered questions in all of cosmology. 47. What lies beyond the observable universe? Imagine standing alone in the middle of a vast ocean. No matter where you look, the horizon forms a perfect circle around you. It may feel like the end of the world, but you know it isn't. There is simply more ocean beyond your view. Now, replace the ocean with the universe. Everything humanity has ever observed, every star, every galaxy, every black hole exists within an invisible boundary known as the observable universe. This immense sphere extends about 46.5 billion light-years in every direction. It contains hundreds of billions of galaxies and represents the farthest reaches of light that has had enough time to reach us since the Big Bang began approximately 13.8 billion years ago. But what lies beyond that cosmic horizon? The truth is both fascinating and frustrating. We don't know. The observable universe is not a physical wall or the edge of space. It is simply the limit of what light has been able to reveal. Because the universe has a finite age and light travels at a finite speed, there are regions so distant that their light is still making its journey toward us. Those places exist beyond our current view, hidden not by distance alone, but by time itself. The simplest possibility is that the universe continues much as it does here. Beyond the horizon may lie countless more galaxies, stars, planets, and perhaps civilizations, stretching across an unimaginably larger cosmos. If the universe is infinite, then our observable bubble is merely an infinitesimal fragment of an endless expanse. But some theories suggest something even stranger. According to cosmic inflation, the universe expanded at an extraordinary rate during the first fraction of a second after the Big Bang. If inflation is correct, the universe beyond our horizon could be vastly larger than we ever imagined, so immense that the observable universe is like a single grain of sand on an endless beach. Other hypotheses venture even further. Some physicists propose that beyond our observable region, the laws of physics might differ slightly. Fundamental constants could have different values, or entirely separate cosmic domains might exist, each with its own unique properties. In the most speculative models, our observable universe could be just one tiny bubble within a much larger multiverse. Can we ever find out? Perhaps not directly. Because the universe continues to expand, many distant regions are receding from us faster than light due to the expansion of space itself. Their light may never reach Earth, placing them permanently beyond our observational reach. This is the ultimate cosmic horizon, not merely a limit of technology, but possibly a limit imposed by the universe itself. Beyond it may lie infinite galaxies, unfamiliar physics, or realities we cannot yet imagine. Every time we build a more powerful telescope, we push deeper into the known cosmos. Yet the greatest mystery remains untouched. Beyond the edge of what we can see lies a universe that may forever remain invisible, waiting in silence just beyond the horizon of human knowledge. 46. Why does the universe look so uniform? Horizon problem. Imagine heating 2 cups of coffee. Leave one in your kitchen and send the other to the opposite side of the Earth. Years later, If you discovered they were exactly the same temperature, you would assume they had somehow exchanged heat or shared information. Now imagine something far more astonishing. The universe contains regions separated by billions of light years, so distant that not even light, the fastest thing in existence, could have traveled between them since the beginning of time. Yet when astronomers measure the faint glow left behind by the Big Bang, known as the cosmic microwave background, they find something extraordinary. No matter where they look, the temperature is almost perfectly identical, differing by only about 1 part in 100,000. How is that possible? This puzzle is known as the horizon problem, and it strikes at the heart of our understanding of the early universe. According to the standard Big Bang model, the universe began about 13.8 billion years ago and has been expanding ever since. In its earliest moments, distant regions of today's universe were simply too far apart for light or any signal to travel between them. They should never have been able to exchange energy or reach the same temperature. And yet, somehow, they did. It's as if billions of cosmic neighborhoods, forever isolated from one another, all agreed on the exact same thermostat. For decades, this contradiction baffled cosmologists. Then, in the early 1980s, physicists proposed a bold solution known as cosmic inflation. The idea is breathtaking. Before the universe entered the expansion we observe today, it may have experienced an unimaginably brief period of explosive growth. In less than 1/trillionth of a second, space itself expanded faster than the speed of light, not because anything moved through space that quickly, but because space itself stretched. Before this dramatic expansion, the entire observable universe was compressed into an incredibly tiny region. Everything was close enough to interact, exchange energy, and reach a nearly uniform temperature. Inflation then rapidly stretched that tiny, well-mixed region into the enormous cosmos we see today, preserving its remarkable uniformity across billions of light years. It is an elegant explanation, but not a complete one. No one knows what caused inflation, what force drove it, or why it stopped when it did. Some physicists even question whether inflation is the whole story, proposing alternative theories that challenge our deepest assumptions about the birth of the cosmos. The horizon problem reminds us that the universe is not only vast, it is astonishingly coordinated in ways that seem almost impossible. Every direction we look carries the same ancient thermal fingerprint, a silent message from the dawn of time. And somewhere within that nearly perfect uniformity may lie the secret of how the universe itself came to be. 45. Did cosmic inflation really happen? Imagine compressing everything you can see, the Milky Way, every distant galaxy, every atom of matter in the observable universe, into a region smaller than a single proton. Now imagine that, in an instant so brief, it defies intuition, that tiny region explodes outward, expanding not at the speed of light, but far faster. It sounds like science fiction. Yet this astonishing idea lies at the heart of one of modern cosmology's most influential theories, cosmic inflation. According to the inflationary model, the universe underwent an extraordinary burst of expansion during the first tiny fraction of a second after the Big Bang. In less than 1 divided by 100 quintillion seconds, space itself expanded by an unimaginable factor, stretching a microscopic patch of the cosmos into a region large enough to eventually become the observable universe. This wasn't an explosion through space. It was space itself expanding. The theory was proposed in the early 1980s to solve several troubling mysteries. Why does the universe appear almost perfectly uniform in every direction? Why is space so remarkably flat? Why don't we observe exotic relics, such as magnetic monopoles, that some theories predict should be abundant? Inflation seemed to answer all of these questions at once. If the observable universe once occupied a tiny, well-connected region, it could naturally reach a nearly uniform temperature before being stretched across billions of light years. Inflation would also smooth out any large-scale curvature, making the universe appear astonishingly flat today. Even hypothetical particles created before inflation would have been diluted to near invisibility. It was an elegant solution, and one that made testable predictions. Decades later, astronomers studying the cosmic microwave background, the ancient afterglow of the Big Bang, discovered subtle patterns that closely matched those predicted by inflation. Tiny quantum fluctuations in the infant universe appear to have been stretched into the seeds that eventually formed galaxies, clusters, and the vast cosmic web we observe today. But despite its remarkable success, one profound question remains unanswered. What caused inflation? No one knows what field or particle triggered this explosive expansion. Physicists often refer to a hypothetical inflattened field, but its true nature remains completely unknown. Even more mysterious, why did inflation begin at exactly the right moment? And perhaps most puzzling of all, why did it stop? Had inflation continued forever, stars, galaxies, and even atoms would never have formed. Some researchers propose that inflation is only one chapter in a much larger story, perhaps involving multiple universes or an eternal process that continuously creates new cosmic regions. Others believe an entirely different theory may eventually replace inflation altogether. Cosmic inflation remains one of the most compelling ideas in modern science, a theory powerful enough to explain the large-scale structure of the universe, yet incomplete enough to remind us how much remains hidden. Somewhere in the first unimaginable instant after the birth of the cosmos lies the answer. And until we uncover what truly ignited inflation, the opening moments of our universe will remain one of the greatest mysteries ever contemplated by the human mind. 44. What triggered inflation? The first instant of the universe may have been the most dramatic event in cosmic history. In far less than the blink of an eye, space itself is thought to have expanded by an unimaginable amount, transforming a microscopic region into the foundation of everything we see today. Galaxies, stars, planets, even the atoms in your body may all owe their existence to this incredible episode known as cosmic inflation. But behind this elegant theory lies an even deeper mystery. What triggered inflation in the first place? Imagine finding the remains of an enormous explosion. The debris tells you an explosion happened, but it tells you almost nothing about who lit the fuse. Cosmologists face a similar challenge. The universe bears many fingerprints of inflation, yet the cause of this explosive expansion remains completely unknown. Most physicists believe inflation was driven by a hypothetical entity called the inflattened field. Unlike familiar fields such as electricity or magnetism, the inflattened has never been observed. It exists only as a mathematical idea, an invisible field that may have filled the newborn universe with enormous energy. This energy would have acted like a powerful form of repulsive gravity, forcing space itself to expand at an astonishing rate. But this explanation immediately raises another question. Why did the inflattened field exist at all? No experiment has detected it. No known particle belongs to it. Scientists don't know whether it was a fundamental feature of nature or merely an effective description of something even more profound. In many ways, naming the inflattened is less an answer than a placeholder for a mystery we have yet to solve. Then comes an equally perplexing puzzle. Why did inflation stop? If the process had continued indefinitely, matter would never have condensed into galaxies, stars, or planets. The universe would have remained an empty, rapidly expanding sea of space. Instead, inflation ended almost as suddenly as it began. The immense energy stored in the inflattened field is thought to have been released, flooding the universe with particles and radiation in a process known as reheating. This event set the stage for the familiar Big Bang evolution that followed. Yet no one knows what caused this transition. Some theories suggest the inflattened field decayed like a radioactive substance. Others propose it rolled into a lower energy state, much like a ball settling into a valley. More speculative ideas connect inflation to quantum gravity, string theory, or even collisions between higher dimensional universes. Each possibility is mathematically intriguing, but none has been confirmed. The greatest challenge is that these events unfolded in less than a trillionth of a second after the birth of the cosmos. They occurred at energies far beyond anything humanity can reproduce in a laboratory. So we are left with one of cosmology's most profound unanswered questions. We may understand that inflation happened. We may even understand what it accomplished. But the identity of the cosmic trigger, the mechanism that switched inflation on, and then somehow switched it off, remains hidden in the deepest shadows of the universe's first moment. 43. What happened before the Big Bang? Imagine rewinding the history of the universe. Galaxies drift closer together. Stars disappear. Atoms are crushed into a searing ocean of particles. Time races backward through billions of years until the entire observable universe shrinks into a state of unimaginable density and temperature. Keep rewinding. Eventually, you reach what we call the Big Bang, the moment when space began expanding and the universe as we know it was born. And then comes the question that has fascinated philosophers, scientists, and dreamers for centuries. What happened before the Big Bang? At first glance, it seems like an obvious question. Every event we experience has a cause. Every beginning appears to follow something else. So surely the Big Bang must have had a beginning too. Or did it? According to Einstein's theory of general relativity, space and time are woven together into a single fabric called space-time. As we trace the universe backward, that fabric becomes increasingly compressed until, at the Big Bang, our equations break down completely. In the simplest interpretation, time itself began at that moment. If time began with the Big Bang, then asking what came before, it may be like asking, what's north of the North Pole? The question assumes that before exists when it may not. But many physicists believe the story doesn't end there. One possibility is that the Big Bang was not the beginning, but a transition. Some theories suggest our universe emerged from the collapse of an earlier universe in a cosmic big bounce. Instead of one beginning, the cosmos could cycle endlessly through expansion and contraction, each Big Bang giving birth to the next. Other ideas come from quantum physics. According to certain models, the universe may have arisen from a tiny quantum fluctuation, a spontaneous event in a primordial quantum state. In this picture, space and time themselves could emerge from deeper physical laws that we do not yet understand. Then there are the boldest proposals of all. String theory suggests our universe might have been created when enormous higher dimensional objects, called brains, collided. Inflationary cosmology hints that our universe could be just one bubble in an eternally inflating multiverse, where countless other universes are continually being born. Each theory is mathematically compelling. Each attempts to peer beyond the curtain of the Big Bang. Yet none has been confirmed. The greatest obstacle is that the conditions before, or at the Big Bang, existed at energies far beyond anything we can recreate on Earth. Our most successful theories, general relativity and quantum mechanics, both fail when pushed to these extremes. To truly understand what happened before the Big Bang, humanity may first need a new theory of physics, one capable of uniting gravity with the quantum world. Until then, the first moment of existence remains hidden behind a cosmic veil. Perhaps the Big Bang was the absolute beginning of space and time. Perhaps it was merely the latest chapter in an eternal cosmic story. Or perhaps the very concept of before is an illusion born from the way our minds experience time. Somewhere beyond the limits of our understanding lies the answer to one of the deepest questions ever asked. Did the universe have a beginning, or has reality existed forever in forms we are only beginning to imagine? 42. Did the universe begin from nothing? Imagine stripping away everything. Every galaxy disappears. Every star fades into darkness. Every planet, every atom, every particle vanishes. Space itself dissolves. Time ceases to flow. Even the laws of physics are erased. What remains? Our instincts say the answer is nothing. But modern physics suggests that nothing may be far more mysterious than we ever imagined. One of the deepest questions in cosmology is this: did the universe truly begin from nothing? Or is there something even more fundamental beneath reality itself? For centuries, the idea of creation from nothing belonged to philosophy and theology. Then quantum physics changed the conversation. In the strange world of quantum mechanics, what appears to be empty space is not truly empty. Even the most perfect vacuum imaginable is alive with activity. Tiny fluctuations constantly create and destroy pairs of particles in unimaginably short intervals. These fleeting events occur because uncertainty is woven into the fabric of the quantum world. Some physicists have proposed a remarkable idea. If quantum fluctuations can produce particles from an apparently empty vacuum, could an entire universe emerge in a similar way? According to certain cosmological models, our universe may have originated as a quantum fluctuation, a microscopic event that rapidly expanded through cosmic inflation, eventually becoming the vast cosmos we inhabit today. In this view, the Big Bang was not an explosion into space, but the birth of space itself from a primordial quantum state. Yet this explanation raises an even deeper question. What is the quantum vacuum? Despite its name, it is not absolute nothingness. A quantum vacuum still obeys physical laws. It possesses measurable energy and exists within a mathematical framework described by quantum field theory. So if a universe emerged from a quantum vacuum, where did that vacuum come from? And where did the laws governing it originate? Some researchers argue that the total energy of the universe may actually be zero. The enormous positive energy stored in matter could be perfectly balanced by the negative energy of gravity. In that case, creating a universe might not violate the conservation of energy at all. It would be like borrowing energy from one cosmic account while repaying it with another. Others believe this still avoids the central mystery rather than solving it. If there are laws that allow universes to appear, why do those laws exist? Why is there a quantum vacuum instead of absolute nothing? At the moment, science has no definitive answer. The question reaches beyond cosmology into the foundations of physics itself. To solve it, we may need a theory that unites quantum mechanics with gravity, a theory capable of describing reality before space, before time, and perhaps before the universe itself. Until then, the greatest mystery remains. Did everything arise from nothing? Or have we simply discovered that what we call nothing is actually the deepest and most fundamental layer of reality, a hidden foundation from which the entire cosmos was born? 41. Why does time flow forward? Arrow of time. Close your eyes and imagine watching a movie in reverse. A shattered glass leaps from the floor, each fragment flying back into place until it becomes whole again. Smoke flows neatly back into a candle. Raindrops rise from the ground into dark clouds overhead. Every scene feels deeply unnatural. But why? Surprisingly, the fundamental laws of physics don't strongly distinguish between the past and the future. If you were to film two planets orbiting each other and play the footage backward, it would still obey Newton's laws of motion. Even Einstein's equations work almost perfectly in reverse. On the smallest scales, nature appears remarkably indifferent to the direction of time. Yet our everyday experience tells a completely different story. We remember yesterday, never tomorrow. We grow older, never younger. Ice melts into water, but melted water never spontaneously forms an ice cube on a warm table. Everywhere we look, time seems to move in only one direction. This mystery is known as the arrow of time. The leading explanation comes from one of the most powerful principles in physics, the second law of thermodynamics. It states that entropy, often described as the measure of disorder or disorder, or the number of possible microscopic arrangements, tends to increase over time. Imagine opening a brand new deck of playing cards. It begins in a highly ordered arrangement. Shuffle it once, then again and again. With every shuffle, the cards become increasingly random. Nothing in the laws of physics forbids the deck from eventually returning to its original order, but the odds are so unimaginably small that it effectively never happens. The universe behaves in much the same way. Stars burn their nuclear fuel, mountains erode, eggs break. Heat flows from hot objects to cold ones. Everywhere, entropy increases, giving time its unmistakable direction. But this explanation only pushes the mystery one step deeper. Why did the universe begin in such an extraordinarily low entropy state? The Big Bang appears to have created a cosmos that was astonishingly smooth and highly ordered. This was an incredibly improbable beginning. If the early universe had started in a more typical disordered state, the arrow of time might never have emerged. There would be no galaxies, no stars, no evolution, and perhaps no observers to ask the question. Some physicists believe the answer lies in the nature of gravity. Others suggest hidden quantum laws or entirely new principles of cosmology. A few even speculate that time itself may not be fundamental, but an emergent property arising from deeper structures beyond our current understanding. The arrow of time remains one of the greatest unsolved mysteries in science. Every ticking clock, every heartbeat, every fading star reminds us that the universe has chosen a direction. But why it chose that direction, and why the past and future are so profoundly different, remains hidden within the earliest moments of cosmic history, waiting for a theory that can finally explain why time never looks back. 40. What is dark matter? Imagine standing beneath a sky filled with billions of stars. Every galaxy, every glowing nebula, every planet, every black hole you've ever seen in photographs seems to represent the universe in its entirety, but appearances can be deceiving. What if everything we can see, every atom that forms stars, planets, oceans, and even our own bodies accounts for only about 5% of the cosmos? What if the vast majority of the universe is made of something completely invisible? Welcome to one of the greatest mysteries in modern astronomy, dark matter. The story begins nearly a century ago. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive collection of galaxies bound together by gravity. When he calculated how much visible matter the cluster contained, the numbers didn't add up. The galaxies were moving so fast that the cluster should have flown apart long ago. Something unseen was holding it together. For decades, many scientists remained skeptical. Then, in the 1970s, astronomer Vera Rubin made a remarkable discovery while studying the rotation of spiral galaxies. According to Newton's laws, stars near the outer edges of a galaxy should orbit more slowly than those near the center, where most of the visible mass resides. But they didn't. The outer stars moved just as fast as those much closer to the galactic core, as though they were embedded inside a vast halo of invisible mass extending far beyond the galaxy's visible edge. Since then, the evidence has become overwhelming. Dark matter reveals itself not by emitting light, but through gravity. It bends the paths of light from distant galaxies in a phenomenon known as gravitational lensing. It shapes the formation of galaxies and galaxy clusters. It leaves subtle fingerprints in the cosmic microwave background, the ancient afterglow of the Big Bang. Every observation points to the same astonishing conclusion. Roughly 27% of the universe consists of matter we cannot see. But what is it? Despite decades of research, no one knows. It cannot be ordinary matter hidden in darkness. There simply isn't enough of it. Instead, scientists suspect dark matter is composed of entirely new particles that interact so weakly with normal matter that they pass through planets, stars, and even our own bodies almost without a trace. Candidates include WIMPs, axions, sterile neutrinos, and even primordial black holes. Yet after years of increasingly sensitive experiments, none has been conclusively detected. This has led some physicists to ask an even more radical question. What if dark matter doesn't exist at all? Perhaps our understanding of gravity itself is incomplete, requiring new laws to explain the motions of galaxies. Whether it is an undiscovered particle, a hidden form of matter, or a clue that gravity behaves differently on cosmic scales, dark matter remains one of the universe's deepest enigmas. Every galaxy we see may be only the luminous tip of a much larger, invisible structure. Hidden all around us is a cosmic scaffold we cannot touch, cannot see, and have yet to understand, a silent presence shaping the universe from the shadows. 39. Why haven't we detected dark matter directly? Imagine knowing that something surrounds you every second of your life, something so abundant that it outweighs all the stars and planets we can see by more than 5 to 1. It shapes entire galaxies, bends the path of light across the cosmos, and influences the evolution of the universe itself. Now imagine that despite decades of searching, no one has ever seen it. This is the mystery of dark matter detection. Astronomers are overwhelmingly confident that dark matter exists. Its gravitational fingerprints appear everywhere we look. Galaxies rotate too quickly to be held together by visible matter alone. Massive galaxy clusters bend light through gravitational lensing in ways that ordinary matter cannot explain. Even the delicate patterns in the cosmic microwave background point to an invisible component making up about 27% of the universe. The evidence is compelling. Yet the particles responsible remain completely unknown. The reason is simple and incredibly frustrating. Dark matter appears to interact with ordinary matter almost exclusively through gravity. Unlike atoms, it doesn't emit light, absorb light, or reflect light. It doesn't glow, cast shadows, or leave obvious traces. If trillions of dark matter particles are passing through your body right now, you would never notice. For decades, scientists have built extraordinary experiments to catch even the faintest interaction. Deep beneath mountains and inside abandoned mines, enormous detectors filled with ultra-pure liquid xenon or argon wait in complete darkness. These underground laboratories are shielded from cosmic rays and background radiation, creating some of the quietest environments on Earth. The hope is that one passing dark matter particle might collide with an atomic nucleus, producing a tiny flash of light or a minute burst of energy. So far, the silence has been deafening. Meanwhile, particle accelerators like the Large Hadron Collider have searched for dark matter by smashing protons together at incredible energies. If dark matter particles could be created in these collisions, they would escape the detectors unseen, revealing themselves only through missing energy. Yet after years of data, no confirmed signal has emerged. Astronomers have also turned the universe into a giant laboratory. They search for gamma rays, X-rays, and other high-energy particles that might be produced if dark matter particles collide and annihilate each other in space. Once again, the evidence remains inconclusive. Every failed experiment forces scientists to rethink their assumptions. Perhaps dark matter is far lighter than expected, like the hypothetical axion. Perhaps it interacts even more weakly than current detectors can measure. Or perhaps the particles we've been searching for simply don't exist, and our theory of gravity needs to be rewritten. The absence of detection is not proof that dark matter is imaginary. Instead, it reminds us that nature often refuses to reveal its secrets easily. Somewhere in the vast darkness of the cosmos, the answer is waiting. Whether it comes from a deeper mine, a more powerful accelerator, a next-generation space telescope, or an entirely new idea, Solving the mystery of dark matter could transform our understanding of the universe and reveal the invisible substance that has shaped cosmic history from the very beginning. 38. Are axions real? Imagine that the greatest mystery in the universe could be solved by one of the smallest particles ever imagined. A particle so incredibly light and so weakly interacting that trillions of them might be passing through your body every second without leaving the slightest trace. This mysterious particle is known as the axion, and if it exists, it could finally reveal the true identity of dark matter. The story of the axion begins not with dark matter, but with an entirely different puzzle in particle physics. In the 1970s, physicists noticed something deeply unsettling. According to the equations of the Standard Model, the strong nuclear force should violate a fundamental symmetry known as CP symmetry. If it did, particles like the neutron would possess a measurable electric dipole moment. But after decades of increasingly precise experiments, no such violation was found. It was as if nature had somehow fine-tuned the universe to avoid this outcome. In 1977, physicists Roberto Peccei and Helen Quinn proposed an elegant solution. Their theory introduced a new field permeating all of space. A few years later, researchers realized that this field should produce an entirely new particle, the axion. At first, the axion seemed like little more than a mathematical curiosity. Then cosmologists made a startling discovery. The properties predicted for axions matched many of the requirements for dark matter. They would carry mass, interact only extremely weakly with ordinary matter, and have been created in enormous numbers during the earliest moments after the Big Bang. Together, they could form the invisible gravitational scaffold holding galaxies together. Suddenly, a particle invented to solve one mystery appeared capable of solving another. So why haven't we found it? Because axions are extraordinarily elusive. Unlike familiar particles, axions would barely interact with light or matter. Detecting one is like trying to hear a whisper during a hurricane. Scientists have therefore devised ingenious experiments to search for their faint signatures. One of the most promising approaches places an ultra-sensitive microwave cavity inside an immensely powerful magnetic field. If axions pass through this field, theory predicts that a tiny fraction could transform into microwave photon signals, so faint they are almost indistinguishable from background noise. Other experiments point giant magnets toward the sun, hoping to capture axions that may be produced in its blazing core. Astronomers also search for subtle effects in neutron stars, black holes, and the evolution of distant galaxies that might reveal the particle's hidden influence. So far, every search has come up empty. Yet the hunt continues because the possible reward is extraordinary. Finding the axion would not simply identify dark matter. It would confirm an entirely new field of nature, solve one of particle physics' oldest puzzles, and reveal that the universe has been filled with invisible particles since the dawn of time. Somewhere, hidden in the silence between the stars, the axion may already be there quietly shaping galaxies, guiding cosmic evolution, and waiting for humanity to build an instrument sensitive enough to hear its almost imperceptible voice. 37. Do sterile neutrinos exist? Imagine a particle so elusive that 100 trillion of them pass through your body every second, almost all without leaving a trace. These ghostly particles are called neutrinos, and they are among the most mysterious inhabitants of the universe. But what if even these nearly invisible particles have an even more secretive cousin? A particle so detached from the rest of reality that it doesn't interact through the weak nuclear force, doesn't emit light, and may reveal itself only through gravity. This hypothetical particle is known as the sterile neutrino. Unlike the three known types or flavors of neutrinos, sterile neutrinos would be almost completely invisible. Ordinary neutrinos can occasionally collide with matter through the weak nuclear force. allowing scientists to detect them in massive underground observatories. Sterile neutrinos, however, would ignore even this interaction. If they exist, they would drift through the universe almost entirely unnoticed, communicating with the rest of the cosmos only through gravity, and perhaps by subtly mixing with ordinary neutrinos. So why do physicists take such an extraordinary idea seriously? Because the universe keeps presenting puzzles that the standard model of particle physics cannot fully explain. One of those puzzles is dark matter. While ordinary neutrinos are far too light and move too quickly to account for the unseen mass holding galaxies together, a heavier sterile neutrino could behave very differently. Formed during the earliest moments after the Big Bang, billions upon billions of these particles could still fill the universe today, creating the invisible gravitational framework that shapes galaxies and galaxy clusters. Sterile neutrinos might also help explain why ordinary neutrinos have mass at all. In one leading theory, known as the seesaw mechanism, extremely heavy sterile neutrinos naturally give rise to the tiny masses of the familiar neutrinos we observe. If true, these invisible particles would be quietly influencing physics at the deepest level. There are even hints, though far from conclusive, that sterile neutrinos may have left subtle fingerprints in experimental data. Over the years, several neutrino experiments have detected small anomalies that don't fit neatly into existing theories. While many of these signals have later been challenged or explained by other effects, they continue to inspire new investigations. The search itself is remarkably difficult. Scientists build enormous neutrino detectors deep underground, shielded from cosmic radiation, hoping to observe tiny changes in neutrino behavior that could reveal sterile counterparts. Astronomers also study X-rays from distant galaxies and the large-scale structure of the universe, looking for indirect evidence that sterile neutrinos once existed in abundance. So far, no experiment has provided definitive proof. Yet the possibility remains tantalizing. If sterile neutrinos are discovered, they could connect particle physics, cosmology, and the origin of dark matter in a single elegant framework. A particle that almost never interacts with the visible universe may turn out to be one of its most important architects, an invisible ghost that has shaped the cosmos since the dawn of time, hidden in plain sight all along. 36. Could primordial black holes be dark matter? Imagine a black hole older than every galaxy in the universe. Not one formed from the collapse of a dying star, but a black hole born in the first fraction of a second after the Big Bang, before the first atoms existed, before the first stars ignited, before light itself could travel freely through space. What if these ancient objects are still out there today, silently drifting through the cosmos? And what if they are the true identity of dark matter? For decades, physicists have searched for an undiscovered particle to explain the invisible mass that holds galaxies together. Candidates such as WIMPs, axions, and sterile neutrinos have inspired some of the most sensitive experiments ever built. Yet despite decades of searching, no dark matter particle has been conclusively detected. This has led some scientists to consider a radically different possibility. Perhaps dark matter isn't made of particles at all. Perhaps it is made of primordial black holes. Unlike ordinary black holes, which form when massive stars exhaust their fuel and collapse under their own gravity, primordial black holes would have formed in the chaotic moments immediately after the Big Bang. During this unimaginably hot and dense era, tiny fluctuations in the density of matter and energy may have been compressed so intensely that gravity overwhelmed every other force, creating miniature black holes throughout the newborn universe. These objects could have been astonishingly diverse. Some might have been smaller than an atom and evaporated long ago through Hawking radiation. Others could have survived for billions of years, quietly orbiting through galaxies without emitting any light. Because black holes interact through gravity alone, they naturally possess one of dark matter's defining characteristics: They are invisible. If enough primordial black holes survived, they could provide the missing mass responsible for the rapid rotation of galaxies and the formation of the vast cosmic web. But how can we search for something that emits no light? Astronomers look for their gravitational fingerprints. One method, called gravitational microlensing, monitors millions of distant stars. If an unseen black hole passes between Earth and a background star, its gravity briefly magnifies the star's light like a cosmic lens. Other searches analyze gravitational waves detected by observatories such as LIGO, asking whether some of the black hole mergers we observe today involve primordial black holes rather than the remnants of dead stars. So far, the results have been intriguing but inconclusive. Many possible mass ranges have already been ruled out. Yet there are still windows where primordial black holes could account for part, or perhaps even all, of dark matter. New observations continue to narrow the possibilities. If this hypothesis is correct, the implications would be extraordinary. The universe's missing mass would not consist of exotic particles waiting to be discovered in underground laboratories. Instead, it would be hidden inside billions upon billions of ancient black holes relics from the universe's first heartbeat. The greatest mystery in cosmology might not be invisible particles at all, but invisible worlds forged in the first moments of existence, silently shaping the universe for nearly 14 billion years. 35. What is dark energy? Imagine throwing a ball high into the air. At first, it rises quickly. Then gravity begins to slow it down. Eventually, it stops, hangs motionless for a brief instant, and falls back to Earth. For centuries, scientists expected the universe to behave in much the same way. The Big Bang launched galaxies outward nearly 13.8 billion years ago. Gravity, generated by all the matter in the cosmos, should have been steadily slowing that expansion ever since. The only question was how much. Would the universe eventually stop expanding? Would it collapse back into a big crunch? Or would it continue expanding forever, growing ever slower? Then, in 1998, astronomers made one of the most shocking discoveries in the history of science. By studying distant exploding stars known as Type Ia supernovae, two independent research teams found that the universe wasn't slowing down at all. It was speeding up. Instead of acting like a ball losing momentum, the universe was behaving as though an invisible force was continuously pushing galaxies farther apart. The farther away they were, the faster they seemed to recede. Something was overpowering gravity on the largest scales imaginable. Scientists gave this mysterious phenomenon a simple name: dark energy. Despite its name, dark energy is not known to be a particle or even a conventional form of energy. It is simply the label we give to whatever is driving the accelerated expansion of the universe. Today, observations suggest that dark energy makes up an astonishing 68% of the total cosmic energy budget. Ordinary matter, the stars, planets, gas clouds, and every living thing accounts for less than 5%. Even dark matter contributes only about 27%. In other words, nearly 7/10 of the universe is something we don't understand. So what could dark energy actually be? One possibility is that it is Einstein's cosmological constant, a tiny amount of energy embedded in empty space itself. Ironically, Einstein introduced this idea in 1917 to keep the universe static, only to later abandon it after the discovery of cosmic expansion. Decades later, his discarded concept returned as a leading explanation for one of the greatest mysteries in cosmology. Other physicists believe dark energy may be a dynamic field that changes over time, a phenomenon sometimes called quintessence. More radical theories suggest that dark energy isn't a substance at all, but evidence that our understanding of gravity breaks down across the vast distances between galaxies. The challenge is that dark energy cannot be observed directly. We cannot collect it in a laboratory or detect it with a telescope. We infer its existence only through its influence on the expansion of the universe itself. Every measurement of distant galaxies, every map of the cosmic microwave background, and every survey of the large-scale structure of the cosmos points toward the same astonishing conclusion. Something unseen is dominating the fate of the universe. Dark energy is more than a scientific mystery. It is the invisible force that may determine the ultimate destiny of everything that exists. Whether it is woven into the fabric of empty space, born from unknown quantum fields, or a sign that our deepest theories are incomplete, dark energy reminds us of a humbling truth. Most of the universe remains hidden, and the greatest force shaping the cosmos may be one we have only just begun to recognize. 34. Is dark energy constant? In 1917, Albert Einstein introduced a single term into his equations that he would later call his greatest blunder. It was a mathematical constant designed to keep the universe perfectly still, preventing gravity from pulling everything together. Years later, astronomers discovered that the universe wasn't static at all, it was expanding. Einstein abandoned the idea, believing it was unnecessary. But nearly a century later, that forgotten constant made an astonishing comeback. In 1998, astronomers found that the expansion of the universe is not slowing down, it is accelerating. Some mysterious force is pushing galaxies farther apart with increasing speed. The simplest explanation is that Einstein's discarded constant was real all along. But what if it isn't? This question lies at the heart of one of cosmology's greatest mysteries. Is dark energy truly constant? If dark energy is Einstein's cosmological constant, then it is a permanent property of empty space itself. Every cubic centimeter of the vacuum would contain the same tiny amount of energy. And as the universe expands, more space would simply mean more dark energy. Its strength would remain unchanged for billions or even trillions of years, causing galaxies to drift ever farther apart in a slow but relentless expansion. It's an elegant idea. Yet nature doesn't always choose the simplest explanation. Some physicists believe dark energy could instead be a dynamic field known as quintessence. Unlike a cosmological constant, quintessence could evolve over time. Its strength might gradually weaken, strengthen, or even reverse direction as the universe ages. It's an elegant idea. Yet nature doesn't always choose the simplest explanation. Some physicists believe dark energy could instead be a dynamic field known as quintessence. Unlike a cosmological constant, quintessence could evolve over time. Its strength might gradually weaken, strengthen, or even reverse direction as the universe ages. If that's true, the future of the cosmos could be dramatically different. A weakening dark energy might allow gravity to regain control, eventually slowing or even halting cosmic expansion. A strengthening dark energy, on the other hand, could lead to one of the most terrifying scenarios in cosmology, the Big Rip. In that future, galaxies would separate, stars would be torn from their galaxies, planets from their stars, and eventually even atoms themselves would be pulled apart by the relentless expansion of space. So how can we tell which picture is correct? Astronomers are turning the universe into a giant laboratory. By mapping millions of galaxies, observing distant supernovae, and studying the faint glow of the cosmic microwave background, scientists are measuring how the expansion of the universe has changed over billions of years. Each new observation places tighter constraints on dark energy's behavior. So far, the evidence suggests that dark energy behaves remarkably like a cosmological constant. But the measurements are not yet precise enough to rule out subtle changes over cosmic time. Even a tiny deviation could signal entirely new physics beyond Einstein's theory. The answer matters because it determines not only what dark energy is, but how the universe will end. Is dark energy an unchanging feature woven into the fabric of space-time since the beginning of time? Or is it a living cosmic field, quietly evolving as the universe grows older? Somewhere among the most distant galaxies lies the answer. And until we find it, the force that dominates nearly 70% of the cosmos remains one of the greatest mysteries ever discovered. 33. Will dark energy destroy the universe? Big Rip. Imagine waking up in a universe where gravity is slowly losing its grip. At first, nothing seems unusual. Galaxies continue drifting apart, just as they have for billions of years. But over unimaginable stretches of time, the expansion of the universe begins to accelerate faster and faster. Entire galaxy clusters unravel. Stars are ripped away from their galaxies. Planets break free from their stars. Eventually, even the atoms that make up your body can no longer hold together. This chilling scenario is known as the Big Rip, one of the most dramatic predictions in modern cosmology. The story begins with dark energy, the mysterious phenomenon responsible for the accelerating expansion of the universe. Today, dark energy appears to make up nearly 68% of the cosmos. Its true nature remains unknown, but so far, observations suggest it behaves almost like a constant property of empty space. If that remains true, the universe will likely continue expanding forever, becoming colder, darker, and more isolated over trillions of years. But what if dark energy isn't constant? Some theoretical models propose that dark energy could actually grow stronger over time. If its repulsive effect increases instead of remaining stable, there may come a point when it overwhelms every force in nature, including gravity, electromagnetism, and even the strong nuclear force that binds atomic nuclei together. The destruction would happen in stages. First, galaxy clusters would no longer be able to hold themselves together. Their member galaxies would drift apart into an ever-expanding void. Millions of years later, individual galaxies like the Milky Way would begin to disintegrate. Stars that have orbited peacefully for billions of years would be flung into the darkness of intergalactic space. As the expansion continued to intensify, planetary systems would become unstable. The Earth would lose its orbit around the Sun, and the Moon would escape Earth's gravity. Then, in the final moments, the fabric of reality itself would begin to unravel. Planets would be torn apart. Molecules would split into individual atoms. Atoms would lose their electrons. Even the protons and neutrons inside atomic nuclei might no longer survive. In the last instant before the end, space itself would expand so violently that every known structure in the universe would cease to exist. Fortunately, there is an important reason for optimism. Current astronomical observations do not indicate that the Big Rip is inevitable. Measurements of distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies are all consistent with dark energy behaving very much like Einstein's cosmological constant, a stable form of energy that does not appear to grow stronger over time. Yet the mystery remains unresolved. Even a tiny deviation from today's measurements could completely change the universe's ultimate fate. Future observatories may reveal whether dark energy is truly constant or quietly evolving in ways we have yet to detect. The Big Rip reminds us that the destiny of the cosmos depends on something we still cannot explain. Hidden within the silent expansion of space may be a force powerful enough not only to shape the universe, but, one day, to tear the entire cosmos apart, from the largest galaxy to the smallest particle, leaving nothing behind but an endlessly expanding sea of empty spacetime. 32. Why is the cosmological constant so small? Imagine calculating the weight of a feather and getting the mass of an entire galaxy. Not because you made a mistake, but because your most trusted theory insisted that was the correct answer. This is the astonishing situation physicists face when they try to understand one of the universe's greatest mysteries, a cosmological constant. When astronomers discovered in 1998 that the universe's expansion is accelerating, The simplest explanation was one Albert Einstein had proposed decades earlier. Empty space itself possesses a tiny amount of energy. This energy, known as the cosmological constant, acts as a gentle repulsive force, pushing galaxies farther apart as the universe expands. The idea fits the observations remarkably well. But then quantum physics enters the picture. According to quantum field theory, empty space is not truly empty. Even the perfect vacuum is alive with restless activity. Quantum fields constantly fluctuate, creating and destroying virtual particles in fleeting moments. Every one of these fluctuations contributes a tiny amount of energy to the vacuum. Individually, these contributions are insignificant. Together, they become a catastrophe. When physicists add them all together, the predicted energy of empty space is about 10 to the power of 120 times larger than the value astronomers actually observe. That is a 1 followed by 120 zeros, the largest known disagreement between theory and observation in the history of science. To grasp how enormous this mismatch is, imagine predicting the distance between New York and Los Angeles, and being wrong by more than the size of the entire observable universe. Somehow, almost all of the vacuum energy appears to cancel itself out with extraordinary precision, leaving behind only the tiny remnant that drives the expansion of the cosmos today. But why? No one knows. Some physicists believe an undiscovered symmetry of nature forces the vacuum energy to nearly vanish. Others suggest that quantum gravity or string theory will eventually reveal the missing mechanism. Another controversial idea comes from the multiverse. If countless universes exist with different values of the cosmological constant, intelligent observers would naturally find themselves in one where the value is small enough for galaxies, stars, and life to form. This explanation, known as the anthropic principle, remains deeply debated because it may be impossible to test directly. The cosmological constant problem is more than a mathematical curiosity. It exposes a profound conflict between our two greatest theories, quantum mechanics and general relativity. Each has transformed our understanding of reality. Yet when they describe the energy of empty space, they disagree by an almost unimaginable amount. Somewhere within that staggering discrepancy may lie the next revolution in physics. Until we understand why the cosmological constant is so extraordinarily small, we cannot claim to fully understand the vacuum, gravity, or perhaps even the universe itself. 31. Why are dark matter and dark energy so balanced today? Coincidence problem. Imagine arriving at a theater just as the curtain rises for the most important scene of the play. You didn't plan it. The timing seems almost impossibly perfect. Now imagine that same coincidence occurring on a cosmic scale. Today, our universe appears to exist at an extraordinarily special moment in its 13.8 billion year history. It is an era in which dark matter and dark energy exert comparable influence over the evolution of the cosmos. This is known as the coincidence problem, and it may be one of the strangest puzzles in modern cosmology. To understand why, we need to travel through cosmic history. Shortly after the Big Bang, the universe was dominated by radiation. As it expanded and cooled, matter gradually became the dominant ingredient. Ordinary matter and dark matter worked together through gravity, pulling gas into dense regions where the first stars and galaxies were born. For billions of years, gravity controlled the universe's evolution. Dark energy was present, but almost irrelevant. Unlike matter, which becomes more spread out as the universe expands, dark energy appears to maintain nearly the same density throughout space. As galaxies drift farther apart, matter grows increasingly dilute, while dark energy remains almost unchanged. Eventually, a remarkable transition occurred. Roughly 5 billion years ago, dark energy became strong enough to overcome gravity, causing the expansion of the universe to accelerate. Here is the mystery. This transition happened during the brief era in which we exist. If intelligent observers had evolved several billion years earlier, dark energy would have seemed insignificant. Several trillion years from now, matter will be so diluted that dark energy will completely dominate the universe. The period when both contribute comparable effects is astonishingly short in cosmic history. So why are we living precisely now? Is it an incredible coincidence, or does it point toward a deeper law of nature? Some physicists argue that there is no mystery at all. According to the anthropic principle, observers can only emerge during the relatively narrow window when galaxies, stars, and stable planetary systems exist. In that view, our timing is simply a consequence of the conditions required for intelligent life. Others suspect the coincidence hints at entirely new physics. Perhaps dark matter and dark energy are not independent after all. Some theories suggest they interact through hidden forces, evolving together over billions of years. Others propose that dark energy itself changes over time, naturally creating the balance we observe today. So far, however, no theory has been confirmed. The coincidence problem reminds us that understanding what dark matter and dark energy are may not be enough. We must also understand why they dominate the universe in exactly the proportions we observe at this particular moment in cosmic history. Perhaps our existence during this extraordinary era is nothing more than chance. Or perhaps it is one of the universe's most subtle clues pointing toward a deeper connection between the two invisible ingredients that together control 95% of the cosmos. 30. Why are there more matter than antimatter? Imagine pressing the reset button on the universe. The Big Bang erupts in a flash of unimaginable energy. In the first moments after its birth, particles begin to emerge from that searing fireball. For every electron, a positron appears. For every proton, an antiproton is created. Matter and antimatter are born in perfect pairs, equal in every respect except one, their electric charge. According to the known laws of physics, they should have existed in exactly equal amounts. And if they had, this story would end almost immediately. Whenever a particle meets its antimatter counterpart, they annihilate each other in a burst of pure energy. If the early universe contained equal quantities of matter and antimatter, every particle should have found its opposite. The result would have been a universe filled with radiation, but no stars, no galaxies, no planets, and certainly no life. Yet here we are. Every atom in your body, every mountain on Earth, every star in the night sky is made almost entirely of matter. Antimatter exists today only in tiny quantities, produced in high-energy collisions or radioactive decay before disappearing almost instantly. So what happened? Somewhere during the universe's earliest moments, matter gained an incredibly small advantage. For roughly every billion pairs of matter and antimatter particles, there may have been just one extra particle of matter. After nearly all the particles annihilated each other, that tiny surplus remained. That single survivor in every billion became everything we see in the universe today. But where did that imbalance come from? Physicists believe the answer lies in a subtle phenomenon called CP violation. In certain particle interactions, nature appears to treat matter and antimatter slightly differently. Experiments involving particles known as kaons and B mesons have confirmed that CP symmetry is indeed violated. Unfortunately, there is a problem. The amount of CP violation observed in the Standard Model is far too small to explain the enormous matter-dominated universe we inhabit. This suggests that something else happened in the earliest moments after the Big Bang, something involving new particles, undiscovered forces, or entirely new laws of physics. Perhaps heavy particles that no longer exist decayed asymmetrically. Perhaps neutrinos hold the key. Or perhaps an unknown process unfolded at energies far beyond anything humanity has ever recreated. The imbalance between matter and antimatter may seem tiny, just one extra particle in a billion. But without it, every galaxy would vanish, every planet would disappear. Every living organism would never have existed. In the end, the greatest mystery is not simply why matter survived, it is why anything survived at all. Somewhere in the first moments of cosmic history, the universe made a choice, or followed a law we have yet to discover, that transformed a perfectly balanced beginning into a universe filled with stars, worlds, and conscious beings capable of asking the question. 29. How did baryogenesis happen? Imagine witnessing the first second of the universe. Temperatures exceed trillions of degrees. Space is flooded with energy so intense that particles and antiparticles are being created and destroyed every instant. The cosmos is a perfect battlefield of symmetry, where matter and antimatter appear in equal numbers and annihilate almost as quickly as they are born. Then something extraordinary happens. The balance breaks. A tiny excess of matter, just one particle out of every billion, survives. That microscopic imbalance eventually becomes every galaxy, every star, every planet, and every living creature in existence. The process responsible for this transformation is known as baryogenesis. It may be the single most important event in the history of the universe. The word baryogenesis literally means the creation of baryons, the family of particles that includes protons and neutrons, the building blocks of ordinary matter. The mystery is that the known laws of physics cannot fully explain how baryogenesis occurred. In 1967, Soviet physicist Andrei Sakharov proposed three conditions that any successful theory of baryogenesis must satisfy. First, reactions must be able to create more baryons than antibaryons. Second, the laws of physics must distinguish between matter and antimatter through processes such as CP violation. Third, these reactions must occur outside thermal equilibrium, preventing matter and antimatter from simply balancing themselves again. These principles became the roadmap for solving one of cosmology's greatest puzzles. Since then, scientists have proposed several fascinating possibilities. One leading idea is electroweak baryogenesis, in which the imbalance formed during a phase transition shortly after the Big Bang, when the electromagnetic and weak nuclear forces became separate. Another possibility is leptogenesis, where heavy, short-lived neutrinos created an excess of leptons. Later, known particle interactions converted part of that excess into the baryons that now make up the visible universe. Some theories even suggest that entirely new particles, existing only at unimaginably high energies, briefly dominated the infant cosmos before disappearing forever. The challenge is that all of these events occurred within the first tiny fractions of a second after the Big Bang, at energy scales far beyond the reach of today's most powerful particle accelerators. That leaves scientists searching for indirect clues. Experiments at the Large Hadron Collider continue probing for new particles and unexpected sources of CP violation. Neutrino observatories investigate whether neutrinos behave differently from antineutrinos. Astronomers study the early universe, hoping to uncover subtle fingerprints left behind by the process that created matter itself. Every discovery brings us closer, but the central mystery remains unsolved. Baryogenesis is more than a chapter in the universe's history. It is the moment when absolute symmetry gave way to existence. Without it, there would be no chemistry, no planets, no sunlight, no life, and no one to wonder how the universe began. Somewhere in the first heartbeat of cosmic time, an almost imperceptible imbalance changed everything. Understanding how that happened may reveal not only why matter exists, but why we exist at all. 28. Why do neutrinos have mass? Imagine a particle so ghostly that trillions pass through your body every second, yet almost none ever collide with a single atom. They stream from the sun, distant supernova, radioactive rocks beneath your feet, and even from the earliest moments after the Big Bang. These elusive travelers are called neutrinos. For decades, physicists believed they were completely massless. In fact, the Standard Model of Particle Physics, the most successful theory ever created to describe the subatomic world, predicted exactly that. It was one of its most confident predictions. And it turned out to be wrong. The mystery began deep underground in enormous neutrino observatories. Scientists noticed something strange. The sun appeared to be producing far fewer electron neutrinos than theory predicted. It wasn't that the sun was malfunctioning. Something was happening to the neutrinos during their 150 million kilometer journey to Earth. The breakthrough came in 1998 at Japan's Super Kamiokande Observatory. Researchers studying neutrinos created by cosmic rays found overwhelming evidence that neutrinos were changing their identities as they traveled. Later experiments, including Canada's Sudbury Neutrino Observatory, confirmed the astonishing discovery. Neutrinos were oscillating. And that revelation carried an unavoidable consequence. According to quantum mechanics, particles can only oscillate between different states if they possess mass. If neutrinos were truly massless, this transformation would be impossible. The discovery forced physicists to rewrite one of the foundations of particle physics, but it also opened an even deeper mystery. Where does that mass come from? Every other known fundamental particle gains its mass through interactions with the Higgs field. Yet neutrinos are astonishingly light millions of times lighter than electrons. Their masses are so tiny that many physicists suspect they arise through an entirely different mechanism. One of the leading ideas is the seesaw mechanism. In this theory, the familiar neutrinos are paired with unimaginably heavy particles known as sterile neutrinos. The enormous mass of these hidden partners naturally makes ordinary neutrinos incredibly light, much like one side of a seesaw rises when the other becomes very heavy. If true, neutrinos may be quietly pointing toward an entirely new layer of physics beyond the Standard Model. Scientists are now building increasingly sensitive experiments to measure neutrino masses with greater precision. Cosmologists also study the large-scale structure of the universe because even these tiny particles subtly influence how galaxies formed over billions of years. The answer matters far beyond particle physics. Neutrinos may hold clues to dark matter, the origin of matter itself, and the earliest moments after the Big Bang. A particle once believed to have no mass at all has become one of the strongest pieces of evidence that our understanding of the universe is incomplete. Sometimes the lightest particles carry the heaviest secrets. 27. Why do neutrinos oscillate? Imagine boarding an airplane as one person and stepping off as someone entirely different. No disguise. No transformation. Simply becoming another version of yourself while no one is watching. In the strange world of quantum physics, something remarkably similar happens every second. Tiny particles called neutrinos constantly change their identities as they travel across the universe. This phenomenon is known as neutrino oscillation, and it is one of the most extraordinary discoveries in modern physics. Neutrinos come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They are created in different environments. The sun mainly produces electron neutrinos. Cosmic rays striking Earth's atmosphere generate muon neutrinos. Powerful particle accelerators can create carefully controlled beams of specific neutrino flavors. For many years, physicists assumed that once a neutrino was created, its identity remained fixed forever. Nature had other plans. As detectors became more sophisticated, scientists noticed something impossible. The sun appeared to be sending too few electron neutrinos to Earth. Atmospheric experiments found fewer muon neutrinos than expected. At first, researchers suspected faulty instruments or errors in theoretical models. Instead, they uncovered an entirely new phenomenon. During their journey through space, neutrinos were changing flavor. An electron neutrino leaving the Sun could arrive at Earth as a muon neutrino or a tau neutrino. It hadn't disappeared. It had transformed. The explanation lies in one of quantum mechanics' strangest ideas. The flavor of a neutrino is not the same as its mass. Instead, each neutrino exists as a quantum mixture of different mass states. As these mass states travel, they evolve at slightly different rates. Their quantum waves gradually drift in and out of sync, causing the probability of detecting each flavor to change continuously. The result is a cosmic dance that unfolds across millions, even billions of kilometers. This discovery revolutionized particle physics because oscillations are only possible if neutrinos possess mass. A particle once thought to be massless turned out to have a tiny but measurable mass, forcing scientists to revise the standard model for the first time in decades. Yet the mystery is far from solved. Why do neutrinos mix in this particular way? Why are their masses so incredibly small? Could there be a fourth type, known as the sterile neutrino, quietly influencing these oscillations? And do neutrinos and antineutrinos oscillate differently, providing clues to why matter dominates over antimatter? Around the world, enormous underground detectors, buried beneath mountains and deep within the Earth, continue to watch for these ghostly particles. Every captured neutrino carries information from the Sun, exploding stars, distant galaxies, and even the first moments after the Big Bang. By changing their identities as they cross the cosmos, neutrinos are sending us a message. Somewhere within their mysterious oscillations lies evidence of new physics, an unseen layer of reality waiting to reshape our understanding of the universe itself. 26. Are there more than 3 neutrino types? Imagine discovering that one of nature's most mysterious particles has been hiding a secret all along. For decades, physicists believed neutrinos came in exactly 3 varieties, or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. These ghost-like particles stream through the universe in unimaginable numbers, passing effortlessly through stars, planets, and even your own body. The standard model of particle physics recognizes only these 3. But what if there is a fourth, or even more? Unlike the known neutrinos, this new type would be even stranger. It would not interact through the weak nuclear force. It would not emit light, absorb light, or leave direct traces inside ordinary detectors. It would be almost completely invisible. Physicists call this hypothetical particle the sterile neutrino. The idea first emerged as scientists struggled to explain puzzling anomalies in neutrino experiments. In the 1990s, the LSND experiment at Los Alamos detected more electron neutrinos than expected. Years later, the Mini-Buini experiment reported a similar excess. Other studies involving nuclear reactors and radioactive sources also hinted that neutrinos might be behaving in ways the 3 known flavors could not fully explain. Could these be glimpses of an undiscovered particle? If sterile neutrinos exist, ordinary neutrinos could occasionally oscillate into this hidden state before transforming back again. During that brief transition, the sterile neutrino would effectively disappear from view, interacting only through gravity and its subtle mixing with ordinary neutrinos. The implications would be extraordinary. Sterile neutrinos could help explain why ordinary neutrinos have such tiny masses. They might contribute to the mysterious dark matter that holds galaxies together. Some theories even suggest they played a role in creating the imbalance between matter and antimatter shortly after the Big Bang. In other words, one invisible particle could connect several of cosmology's greatest mysteries. Yet the evidence remains frustratingly uncertain. Many newer experiments have failed to confirm the earlier anomalies. Others continue to report results that neither clearly support nor completely rule out sterile neutrinos. Around the world, increasingly precise detectors are searching for tiny deviations in neutrino behavior, hoping to settle the question once and for all. It is possible that the earlier signals were caused by unknown experimental effects. It is also possible that they were our first glimpse of physics beyond the standard model. If a fourth neutrino exists, it would represent the first entirely new fundamental particle discovered in decades. It would expand our understanding of matter, reshape particle physics, and perhaps reveal part of the invisible universe that has remained hidden since the dawn of time. Sometimes the greatest discoveries are not made by finding something new. They begin by noticing that something keeps disappearing. 25. What is quantum gravity? Imagine holding two books. Each is one of the greatest scientific achievements in human history. The first explains the motion of planets, the evolution of galaxies, the birth of black holes, and the expansion of the universe. This is Einstein's theory of general relativity, where gravity is not a force, but the curvature of space and time itself. The second describes a world so small that particles can exist in multiple states at once, appear from empty space, and become mysteriously connected across vast distances. This is quantum mechanics, the theory governing atoms and subatomic particles. Individually, these theories are astonishingly successful. Together, they refuse to cooperate. This conflict has become one of the greatest unsolved problems in all of physics. It is known as quantum gravity. The trouble begins in the most extreme places in the universe. Near the center of a black hole, gravity becomes unimaginably intense. At the very beginning of the Big Bang, the entire observable universe was compressed into an incredibly tiny volume. In these environments, both gravity and quantum effects become equally important. But when physicists try to combine Einstein's equations with quantum mechanics, the mathematics collapses into infinities that have no physical meaning. Nature appears to be speaking two different languages. One describes the smooth, continuous fabric of spacetime. The other describes a universe built from discrete quantum probabilities. Somehow, both are correct, and yet neither can fully explain reality on its own. For decades, scientists have searched for a theory that unites them. One leading candidate is string theory, which proposes that fundamental particles are not point-like objects, but tiny vibrating strings. Different patterns of vibration produce the particles and forces we observe. In this picture, gravity naturally emerges alongside quantum physics, potentially unifying all the fundamental forces. Another approach is loop quantum gravity, which suggests that spacetime itself is not continuous. Instead, space may be woven from unimaginably tiny quantum loops, giving the universe a granular structure at the smallest possible scale. Other ideas are even more radical. Some researchers believe spacetime emerges from quantum information itself. Others propose that gravity is not fundamental, but an emergent phenomenon arising from deeper microscopic laws. The challenge is that these effects occur at the Planck scale around. 10 meters far smaller than anything today's technology can directly probe dot, so physicists search indirectly. They study black holes, gravitational waves, the early universe, and subtle quantum effects that might reveal cracks in our current theories. The quest for quantum gravity is about far more than fixing mathematical equations. It is an attempt to uncover the deepest architecture of reality. Somewhere beneath space, beneath time, beneath every particle and every force, there may exist a single elegant framework from which the entire universe emerges. Finding that theory would not simply complete modern physics. It could reveal the true nature of existence itself, answering questions that have remained hidden since the first instant of the cosmos. 24. What happens at the center of a black hole? Imagine falling toward a black hole. At first, nothing seems unusual. If the black hole is enormous, you might cross its event horizon without noticing anything at all. There is no solid surface, No wall of fire, no sudden impact. Behind you, the rest of the universe slowly fades from view. Ahead lies a destination from which nothing, not even light, can ever return. Deep inside, every possible path leads in only one direction: toward the center. According to Einstein's theory of general relativity, that journey ends at a point called a singularity, a place where matter is compressed into infinite density. Space-time is infinitely curved, and the known laws of physics simply cease to work. Infinity. Whenever physicists encounter infinity in an equation, it usually signals that the theory has reached its limit. It doesn't necessarily mean reality contains something truly infinite. Instead, it often means that our mathematical description has broken down. The singularity may be less of a physical object and more of a signpost telling us that something fundamental is missing. The problem is that general relativity describes gravity on the largest scales, while quantum mechanics governs the smallest. Near the center of a black hole, both become equally important. Gravity is unimaginably strong, yet quantum effects can no longer be ignored. Unfortunately, the two theories refuse to fit together. This is why many physicists believe that singularities don't actually exist in nature. Instead, they may be replaced by an unknown quantum structure that only a complete theory of quantum gravity can describe. Some possibilities are astonishing. In loop quantum gravity, space-time itself may become discrete, preventing matter from collapsing into infinite density. In certain models, the crushing collapse could eventually rebound, creating a white hole, a theoretical object that ejects matter instead of trapping it. String theory offers another vision. Instead of collapsing into an infinitely small point, matter might spread into tiny vibrating strings or higher dimensional structures, eliminating the singularity altogether. Other researchers have proposed even stranger ideas. The interior of a black hole could contain a bridge to another region of spacetime, wormhole, or perhaps an entirely new universe, born from the collapse of the old one. For now, these ideas remain speculative. The event horizon hides the black hole's interior from direct observation. No signal can escape to tell us what truly lies within. Yet every time astronomers detect gravitational waves from colliding black holes or capture sharper images of their shadows, they gather clues about the most extreme objects in existence. The center of a black hole is more than a mysterious destination. It is the place where our greatest theories collide and fail. Somewhere beyond the event horizon may lie the key to unifying gravity and quantum mechanics, revealing what space-time really is, and perhaps uncovering a deeper layer of reality that has remained hidden since the beginning of the universe. 23. Where does information go inside a black hole? Imagine taking the greatest library ever built. Every book, every photograph, every memory, every piece of information ever created, now throw it all into a black hole. What happens next? According to Einstein's theory of general relativity, everything that crosses the event horizon is trapped forever. The information describing every particle appears to vanish into the black hole's interior, forever hidden from the outside universe. For decades, that seemed to be the end of the story. Then, in the 1970s, physicist Stephen Hawking made a revolutionary discovery. Using quantum mechanics, Hawking showed that black holes are not completely black. Tiny quantum fluctuations near the event horizon allow them to emit a faint glow known as Hawking radiation. Over unimaginable lengths of time, this radiation slowly drains the black hole's mass until, eventually, the black hole evaporates completely. And that created a crisis. Hawking radiation appears to be completely random. If a black hole eventually disappears, leaving behind only random radiation, then all the information about everything that ever fell inside seems to be permanently erased. That conclusion clashes directly with one of the deepest principles of quantum mechanics. In quantum theory, Information cannot be destroyed. It may become scrambled beyond recognition, but it must always exist in some form. The universe is supposed to be perfectly reversible at its most fundamental level dot, so which theory is wrong? General relativity? Quantum mechanics? Or our understanding of black holes? This puzzle became known as the black hole information paradox, and it has challenged physicists for nearly half a century. Many possible solutions have been proposed. Some researchers believe the information is subtly encoded within Hawking radiation itself, escaping in an extraordinarily scrambled form that is almost impossible to reconstruct. Others argue that information is stored on the black hole's event horizon, leading to the remarkable holographic principle, the idea that the three-dimensional contents of a region may be fully described by information written on its two-dimensional boundary. Even more controversial ideas include firewalls, which would destroy anything crossing the event horizon, or wormholes connecting distant regions of spacetime, allowing information to escape in unexpected ways. Remarkably, recent breakthroughs in quantum information theory suggest Hawking's original conclusion may have been incomplete. Sophisticated calculations indicate that information might gradually leak out during black hole evaporation after all, but exactly how this happens remains one of the hottest topics in theoretical physics. The black hole information paradox is more than a mystery about black holes. It is a battle between the two greatest theories ever devised. Somewhere within this paradox lies the missing link between gravity and quantum mechanics, a clue that could transform our understanding of space, time, and reality itself. When we finally discover where information goes inside a black hole, we may also discover the hidden rules that govern the entire universe. 22. Do white holes exist? Imagine a place in the universe where the laws of gravity seem to run backward. Instead of pulling everything inward, it relentlessly pushes everything out. Matter, light, and energy pour into space, but nothing can ever enter. It sounds like the exact opposite of a black hole. And according to certain solutions of Einstein's equations, such an object is mathematically possible. It is called a white hole. Black holes are among the best-studied objects in modern astronomy. We have photographed their shadows, detected the gravitational waves produced when they collide, and observed stars orbiting invisible giants at the centers of galaxies. White holes, however, are different. No one has ever seen one. The idea emerged naturally from Einstein's theory of general relativity. If the equations describing a black hole are mathematically reversed in time, they produce an object that behaves in the opposite way. Instead of trapping everything behind an event horizon, a white hole possesses a boundary that nothing can cross from the outside. Matter and radiation can escape, but nothing can fall in. In theory, a white hole could suddenly erupt into existence, eject enormous amounts of matter and energy, and then gradually fade away. But if the mathematics allows them, why haven't astronomers found any? One reason is that white holes appear to be extraordinarily unstable. Even the tiniest amount of matter approaching a white hole would seem to disrupt the delicate conditions required for it to exist. In the real universe, filled with gas, dust, radiation, and stray particles, maintaining a perfect white hole may be nearly impossible. Yet the concept refuses to disappear. Some physicists have proposed that white holes could represent the final stage of a black hole's life. According to certain quantum gravity models, matter collapsing inside a black hole might never reach an infinite density singularity. Instead, after an immense period of time, the collapse could reverse, causing the black hole to bounce and release its contents through a white hole. Others have suggested that the Big Bang itself resembled a gigantic white hole, a one-way event in which space, time, matter, and energy suddenly burst into existence. Even more speculative ideas connect white holes to wormholes, proposing that matter, entering a black hole in one region of the universe, could emerge from a white hole, somewhere else, or perhaps in an entirely different universe. So far, however, no observation has confirmed any of these possibilities. Every candidate event has ultimately found more conventional explanations. Still, white holes remain fascinating because they expose the limits of our understanding. They remind us that Einstein's equations permit realities far stranger than anything we have observed. Whether white holes are genuine cosmic objects or merely mathematical curiosities, they challenge us to think beyond the visible universe. Somewhere between theory and observation lies the answer. If white holes do exist, they would transform our understanding of black holes, gravity, and the flow of time itself, revealing that the universe may contain not only cosmic traps, but also cosmic gateways through which reality itself can be reborn. 21. Can wormholes really exist? Imagine folding a sheet of paper. Draw two dots on opposite corners. To an ant crawling across the surface, reaching the second dot would require a long journey. But fold the paper so the two dots touch. Suddenly, a path that once stretched across the page becomes almost instantaneous. Some physicists believe space-time itself might work in a similar way. These hypothetical shortcuts are known as wormholes. First predicted as mathematical solutions to Einstein's theory of general relativity, wormholes are often described as tunnels connecting two distant regions of space and time. Instead of traveling across billions of light years, a spacecraft entering one end of a wormhole could, in principle, emerge almost instantly at the other. It sounds like science fiction. Remarkably, the mathematics says it might be possible. The earliest concept appeared in the 1930s, when Albert Einstein and Nathan Rosen discovered a peculiar solution, now known as the Einstein-Rosen bridge. It linked two separate regions of space-time through a hidden connection. There was one major problem. The bridge would collapse so quickly that nothing, not even light, could pass through it. To create a traversable wormhole, something extraordinary would be required. Calculations suggest the tunnel would need to be held open by negative energy, a form of exotic matter with properties unlike anything found in everyday experience. While tiny amounts of negative energy appear in certain quantum phenomena, no one knows whether enough could ever exist to stabilize a macroscopic wormhole. Even if such matter could be found, other challenges remain. Passing through a wormhole might expose travelers to immense tidal forces, violent radiation, or quantum instabilities capable of destroying the tunnel before anyone reached the other side. Yet the idea continues to captivate physicists because wormholes touch some of the deepest questions in science. Recent research has revealed surprising connections between wormholes and quantum entanglement, the mysterious phenomenon in which particles remain linked across vast distances. Some theorists have even proposed the bold idea, summarized by the phrase I equals EPR, suggesting that wormholes and quantum entanglement may be two different expressions of the same underlying reality. If true, the fabric of spacetime could be far stranger than Einstein ever imagined. Some speculative models go even further, proposing that wormholes might connect entirely different universes, providing bridges across the multiverse itself. At present, however, there is no observational evidence that natural traversable wormholes exist. No telescope has detected one. No spacecraft has traveled through one. For now, wormholes remain elegant mathematical possibilities waiting for nature's verdict. But if even one were ever discovered, it would revolutionize physics overnight. The universe would no longer be limited by ordinary distance. Space, time, and perhaps even separate universes could be woven together by hidden pathways, transforming what we thought was impossible into a fundamental feature of reality itself. 20. Is our universe part of a multiverse? Imagine looking out across a vast ocean. From the shore, you can see only one island. It feels unique, isolated, perhaps even alone. But beyond the horizon may lie thousands, perhaps millions of other islands, forever hidden from view. Now replace that island with our entire universe. What if everything we've ever known, the Milky Way, every galaxy, every star, every atom, and every law of physics is merely one tiny bubble in a far greater cosmic ocean? This breathtaking possibility is known as the multiverse. For centuries, people assumed the universe was everything that exists. But modern physics has opened the door to a far stranger idea. Our universe may be just one of countless others, each with its own history, and perhaps its own laws of nature. The concept emerges from several independent areas of physics. One of the strongest comes from cosmic inflation. According to some versions of inflation, the rapid expansion that followed the Big Bang never completely ended. While inflation stopped in our region, allowing galaxies and stars to form, it may still be continuing elsewhere. As inflation proceeds, it continually creates new bubble universes. Each bubble becomes its own separate cosmos, disconnected from the others by vast expanses of ever-expanding space. Our universe could simply be one bubble among an endless cosmic foam. String theory offers another intriguing possibility. The equations of string theory allow an enormous number of possible vacuum states, perhaps as many as 10 to the power of 500. Each vacuum could produce a universe with different physical constants. In one universe, gravity might be stronger. In another, electrons could be heavier. Some universes might never form stars. Others could collapse almost instantly after they are born. Only a tiny fraction would possess the precise conditions necessary for galaxies, planets, and life. Some physicists argue this may explain why our universe appears so remarkably fine-tuned. If countless universes exist, we naturally find ourselves in one capable of supporting observers. Yet there is a fundamental challenge. How do you test for universes you cannot see? Some researchers search the cosmic microwave background for subtle scars left by collisions between our universe and neighboring bubbles during the earliest moments after the Big Bang. Others look for statistical clues hidden in the values of nature's fundamental constants. So far, however, no convincing evidence has been found. The multiverse remains a fascinating hypothesis, not an established fact. Some scientists embrace it as the natural consequence of modern theories. Others argue that ideas which cannot be directly tested may fall outside the boundaries of science itself. Still, the question refuses to disappear. If our universe is just one chapter in an infinite collection of realities, then everything we call the universe is only a tiny piece of something unimaginably larger. The greatest discovery in human history may not be that we found another planet, another galaxy, or another universe. It may be realizing that our entire cosmos is just one grain of sand on the infinite shore of existence. 19. Are there parallel versions of us? Imagine you're standing at a crossroads. One path leads you home. The other takes you on a journey that changes your life forever. You choose one road, leaving the other behind. Or did you? According to one of the most extraordinary ideas in modern physics, both choices may actually happen. In one universe, you walk home. In another, you take the second path. Both realities continue to exist completely unaware of each other. This astonishing concept is known as the many worlds interpretation of quantum mechanics. The mystery begins with one of quantum physics' strangest features, superposition. Before a quantum particle is measured, it does not appear to occupy a single definite state. Instead, it behaves as though multiple possibilities exist simultaneously. An electron can take many paths at once. A photon can interfere with itself as if it traveled through two openings simultaneously. But the moment we make a measurement, only one outcome is observed. Why? The traditional explanation is that the wave function collapses, forcing nature to choose a single reality. In 1957, physicist Hugh Everett III proposed a radically different idea. What if the wave function never collapses? Instead, every possible outcome actually occurs. Each quantum event causes reality itself to branch into multiple parallel universes. Every decision, every particle interaction, every quantum fluctuation creates new versions of reality, each evolving independently in one universe. A coin lands heads. In another, tails in one. Dinosaurs never became extinct. In another, humanity never evolved. Somewhere, there may even exist versions of you who make different choices at every major moment of life. These aren't copies traveling between universes. They are separate branches of reality that no longer interact. It is a breathtaking idea, but an enormously controversial one. The mathematics of quantum mechanics works perfectly without requiring wave function collapse, making many worlds an elegant interpretation. However, it also predicts an unimaginably vast number of invisible universes that may never be observed directly. Critics argue that if these parallel worlds cannot be detected, the theory may not be scientifically testable. Supporters counter that many worlds simply takes quantum mathematics at face value, without adding extra assumptions about collapse. At present, no experiment has definitively distinguished between many worlds and competing interpretations of quantum mechanics. The debate remains one of the deepest in modern science. If parallel versions of us truly exist, then every possibility allowed by quantum physics may be unfolding somewhere in an ever-branching cosmic tree. Whether these alternate realities are physical worlds or merely mathematical descriptions remains unknown. But if the many worlds interpretation is correct, the universe is far stranger than we ever imagined, not because there is one reality, but because there may be an endless number of them, each telling a different version of the story of existence. 18. Is the universe fine-tuned for life? Imagine turning the dial on the universe just slightly. Not by 1,000%, not even by 1%, but by the tiniest imaginable fraction. Now imagine that single adjustment erasing every galaxy, every star, every planet, and every possibility for life. This extraordinary idea lies at the heart of one of cosmology's greatest mysteries. Is our universe fine-tuned for life? Scientists have discovered that the universe is governed by a collection of physical constants numbers that determine how gravity behaves, how strongly atoms hold together, how fast light travels, and how matter interacts with energy. These constants are not predicted by current physics. They simply exist with remarkably precise values. And here's the mystery. If the strength of gravity were just a little stronger, stars would burn too quickly, exhausting their fuel before planets had time to form. If gravity were slightly weaker, stars might never ignite at all. The electromagnetic force must also fall within an incredibly narrow range. Alter it only slightly, and chemistry as we know, it becomes impossible. The same is true for the strong nuclear force, the weak nuclear force, and even the amount of dark energy filling space. Together, these values create a universe balanced on what appears to be a razor's edge. Coincidence? Some physicists argue that it is exactly that, a coincidence, waiting for a deeper explanation. They believe a future theory of everything may reveal that these constants could never have been any different. Others disagree. Some propose that our universe is just one among countless universes, each born with different physical laws. Most would be barren and lifeless. We simply happen to exist in one of the rare universes where the cosmic settings permit stars, planets, and observers. Still others see something even more profound. They argue that the astonishing precision of these constants suggests purpose rather than chance. While science cannot test philosophical or theological conclusions, the apparent fine-tuning has sparked discussions reaching far beyond physics itself. What makes this mystery so captivating is that every discovery seems to deepen it. The more accurately scientists measure these constants, the more delicately balanced they appear. Modern cosmology has revealed a universe that is not merely orderly, it is astonishingly hospitable to complexity. Yet we still don't know why. Were these numbers inevitable? Random? Or clues pointing toward a deeper layer of reality that we have yet to uncover? The universe remains silent, but every star that shines, every atom in your body, and every question we ask exists because these invisible numbers are exactly what they are. Perhaps someday we'll learn whether the universe was destined to support life, or whether life simply won the greatest cosmic lottery imaginable. 17. Is the anthropic principle the answer? What if the greatest mystery of the universe has a surprisingly simple answer? Not that the universe was designed for us, but that we could only exist in a universe where our existence is possible. This idea is known as the anthropic principle, and despite its simplicity, it has become one of the most debated concepts in modern cosmology. The puzzle begins with a familiar question. Why do the laws of physics seem perfectly suited for life? As scientists uncovered the astonishing precision of the universe's physical constants, many wondered whether this apparent fine-tuning demanded an explanation. Why should gravity, electromagnetism, and the nuclear forces possess exactly the values needed for stars, planets, chemistry, and ultimately living beings? The anthropic principle offers an unexpected perspective. Imagine walking into a room and winning the lottery every single time not. It would seem impossible. But now imagine there are trillions upon trillions of lottery rooms, each with different rules and different outcomes. Eventually, someone is bound to win somewhere. Naturally, that winner will wonder why they were so fortunate. Our universe may be much the same. If an enormous multiverse exists, containing countless universes with different physical constants, then most of those universes would never produce life. No observers would exist there to ask questions. Only in the rare universes where the conditions happen to support observers would anyone be around to notice how perfectly balanced everything appears. In this view, the mystery isn't that our universe supports life. The mystery is simply that we are here to observe it. There are actually two versions of the anthropic principle. The weak anthropic principle states that any observations we make are inevitably limited by the conditions required for our existence. This idea is widely accepted because it reflects an unavoidable observational bias. The strong anthropic principle, however, goes much further. It suggests that the universe must possess properties that allow conscious observers to emerge. Whether this is a profound insight or merely philosophical speculation remains deeply controversial. Critics argue that the anthropic principle explains very little. Instead of revealing why the constants have their values, it may simply restate the obvious. If they were different, we wouldn't be here. Supporters counter that when combined with multiverse theories, it becomes a powerful statistical explanation for cosmic fine-tuning. The truth is that no experiment has yet confirmed either view. The anthropic principle sits at the fascinating boundary where cosmology, philosophy, and probability converge. It reminds us that every scientific observation is made from a unique perspective, one shaped by the extraordinary fact that we exist at all. Perhaps the universe was never designed for observers. Or perhaps observers are the very reason the universe appears exactly as it does. For now, the answer remains hidden among the stars. 16. Could we live inside a simulation? Look around you, the screen in front of you, the air you breathe, the stars scattered across the night sky, every memory you've ever made, every person you've ever loved. What if none of it is fundamentally real? Not fake, but simulated. It sounds like science fiction, yet this astonishing possibility has become one of the most controversial philosophical ideas of the 21st century. Known as the simulation hypothesis, it asks a question that challenges everything we think we know about reality. Could our entire universe be an artificial simulation created by an advanced civilization? The idea begins with a simple observation. Humanity has progressed from primitive computers to immersive virtual worlds in just a few decades. Every year, computer graphics become more realistic, artificial intelligence more sophisticated, and simulations more complex. If technological progress continues for thousands or even millions of years, could a future civilization possess enough computational power to simulate entire planets or entire universes? Some philosophers believe the answer may be yes. If civilizations become capable of creating vast numbers of realistic simulations populated by conscious beings, then simulated minds could eventually outnumber biological ones. Statistically, that would raise an unsettling possibility. It may be far more likely that we are among the simulated observers than the original creators. But if our universe is simulated, could we ever know? Some physicists have speculated that the universe might contain subtle clues. Perhaps space and time are not infinitely smooth, but built from tiny, discrete units like pixels on a digital screen. Others have wondered whether the speed of light or the strange rules of quantum mechanics could reflect the limitations of an unimaginably advanced computational system. So far, however, no convincing evidence has emerged. Every experiment performed to test the laws of nature has continued to support our current understanding of physics. The universe behaves with remarkable consistency, revealing no obvious glitches or hidden source code. Critics argue that the simulation hypothesis is ultimately untestable. If the creators designed the simulation perfectly, any evidence could simply be programmed away. Without a way to falsify the idea, many scientists consider it philosophy rather than science. Yet the hypothesis continues to captivate researchers because it forces us to reconsider the meaning of reality itself. If conscious experiences are genuine, does it matter whether the universe is made of atoms or information? Would love, curiosity, fear, and hope become any less real simply because they emerged inside a simulation? Perhaps reality is exactly what we experience. Or perhaps, somewhere beyond our universe, unimaginable beings are watching countless civilizations unfold across digital cosmoses of their own creation. Until we discover a way to look beyond the boundaries of our universe, one question will remain impossible to ignore. Are we exploring reality, or merely exploring the most sophisticated simulation ever created? 15. Will the universe end in heat death? Every fire eventually fades. Every star exhausts its fuel. Every galaxy slowly changes with time. If the universe has a beginning, does it also have an ending? According to our best understanding of modern cosmology, the answer is yes. But it may not end with a catastrophic explosion or a dramatic collapse. Instead, the universe could fade away so gradually that no living observer would ever witness its final moments. This possible future is known as heat death, the slow and relentless march toward cosmic darkness. Today, the universe is filled with energy flowing from hot places to cold ones. Stars blaze with nuclear fusion, galaxies shine across billions of light years, and life exists because energy is constantly being transformed. But the second law of thermodynamics tells us that entropy, the measure of disorder, always increases. Over unimaginable spans of time, usable energy becomes increasingly scarce. The first stage of this cosmic future begins trillions of years from now. The youngest red dwarf stars, some capable of shining for trillions of years, will finally exhaust their hydrogen fuel. One by one, the last stars will go dark. No new stars will be born, as the gas needed to create them has long since been consumed or scattered into intergalactic space. The universe enters an age of darkness. Galaxies become graveyards, populated by white dwarfs, neutron stars, and black holes silently orbiting through the void. Yet even black holes are not eternal. According to Stephen Hawking's groundbreaking work, black holes slowly lose energy through a process called Hawking radiation. Over periods so vast that ordinary numbers become meaningless, even the largest black holes will evaporate into faint streams of particles. Eventually, almost nothing remains. Only isolated photons, neutrinos, electrons, and other elementary particles drift through an endlessly expanding cosmos. No stars, no planets. No galaxies, no sources of usable energy. The temperature everywhere approaches nearly absolute zero, and all physical processes slow to an almost unimaginable crawl. This is heat death, a universe that has reached maximum entropy, where no meaningful work can be performed because energy is spread almost perfectly evenly throughout space. Could this bleak future be avoided? Some alternative theories suggest the universe might eventually collapse in a big crunch, tear itself apart in a big rip, or even experience repeated cycles of death and rebirth. But current observations indicate that cosmic expansion is accelerating, making heat death the leading prediction under today's cosmological models. Fortunately, this end lies so far in the future that even writing out the number of years would require pages of zeros. For now, the universe remains brilliantly alive. Stars continue to ignite. Galaxies continue to collide. New worlds continue to form. Yet hidden beneath all this beauty, the quiet arrow of time continues its one-way journey toward a future where the lights of the cosmos slowly fade until only silence and darkness remain. 14. Could the universe collapse again? For nearly 14 billion years, the universe has been expanding. Galaxies race away from one another. Space itself stretches in every direction. Every second, the cosmos grows larger than it was the moment before. But what if this expansion is only temporary? What if one day the universe reaches its greatest size, pauses, and begins the long journey back toward its own destruction? This dramatic possibility is known as the Big Crunch, a theory that imagines the universe ending not in cold darkness, but in a fiery collapse. The idea begins with gravity. Gravity is the only fundamental force that acts over enormous cosmic distances, pulling matter together. After the Big Bang, the universe expanded rapidly, but gravity immediately began resisting that expansion. For decades, astronomers wondered whether gravity might eventually become strong enough to halt the universe's growth entirely. Imagine throwing a ball high into the sky. It rises, slows, stops, and falls back to Earth. The Big Crunch proposes that the universe could behave in much the same way. If the total amount of matter and energy in the universe were great enough, gravity could eventually overcome expansion. Galaxies would stop drifting apart. Then they would begin moving closer together. Over billions of years, the entire cosmos would shrink. As space contracted, galaxies would collide with increasing frequency. Temperatures would climb. Radiation would intensify. The night sky would grow brighter as distant galaxies rushed toward one another. Eventually, stars themselves would no longer survive. Matter would become compressed beyond anything we can imagine. Black holes would merge into ever larger giants, swallowing everything around them. The fabric of space would continue collapsing until every galaxy, every star, every planet, and every atom occupied an unimaginably small volume. Would the universe end as an infinitely dense singularity, much like the one thought to exist at the beginning of the Big Bang? No one knows. Modern physics breaks down under such extreme conditions, leaving scientists without a complete description of what would happen in the final moments. For many years, the Big Crunch was considered one of the leading models for the universe's fate. But everything changed in 1998. Astronomers discovered that the universe's expansion is not slowing, it is accelerating. An unknown phenomenon called dark energy appears to be pushing galaxies apart faster over time. If dark energy continues to dominate the cosmos, gravity may never be able to reverse the expansion. Instead of collapsing, the universe may continue growing forever. Does that mean the Big Crunch is impossible? Not necessarily. Some theories suggest dark energy could change over immense spans of time, or that our current understanding of gravity remains incomplete. Until scientists uncover the true nature of dark energy, the possibility cannot be entirely ruled out. The Big Crunch reminds us that the universe's future is still unwritten. Will gravity one day reclaim the cosmos? Or will expansion continue forever, carrying every galaxy beyond the reach of every other? For now, the universe keeps expanding. But the ultimate ending remains one of cosmology's greatest unanswered questions. 13. Does the universe recycle itself? What if the Big Bang was not the beginning? What if our universe was born from the death of another? Imagine a cosmos that never truly begins and never truly ends, a universe caught in an endless cycle of expansion, collapse, and rebirth. This extraordinary idea is known as the Big Bounce, and it challenges one of the most fundamental assumptions in cosmology, that the Big Bang marked the absolute beginning of everything. According to the traditional picture, the universe started nearly 13.8 billion years ago from an incredibly hot, dense state. As we trace cosmic history backward, matter becomes more compressed, temperatures rise without limit, and eventually, our equations predict a singularity, a point where density becomes infinite and the known laws of physics cease to function. But many physicists are uncomfortable with singularities. Infinite density often signals that a theory has reached its limits rather than describing physical reality. This has inspired researchers to explore a different possibility. Perhaps the universe never reached an infinite point at all. In several quantum gravity models, space itself possesses microscopic properties that become important under extreme conditions. As the universe contracts, these quantum effects could generate a powerful repulsive force, preventing total collapse. Instead of ending in a singularity, the universe would rebound. Like a perfectly compressed spring suddenly released, the collapsing cosmos would reverse direction, expanding once again in a new Big Bang. This rebound is the bounce. In this picture, our universe could simply be the latest chapter in an endless cosmic sequence. Before our Big Bang, another universe may have existed. It expanded for billions of years, eventually contracted, and then bounced into the universe we now inhabit. If true, every cycle could erase much of the previous universe's structure while still preserving subtle clues. Scientists have searched for such evidence in the cosmic microwave background, the faint afterglow of the Big Bang. Some researchers have suggested that unusual patterns or tiny anomalies might hint at events before our own cosmic expansion. So far, however, no observation has provided definitive proof. The Big Bounce also offers an elegant answer to one of cosmology's oldest questions. If every universe emerges from the collapse of a previous one, then asking what happened before the Big Bang may no longer make sense. The Big Bang would not be the beginning of time. It would simply be another transition in an eternal cycle. Yet enormous challenges remain. No existing theory has successfully unified quantum mechanics and gravity into a complete framework capable of describing a bounce with certainty. Competing models make different predictions, and current observations remain consistent with several possible cosmic histories. For now, the Big Bounce remains one of the most fascinating ideas in theoretical physics. Perhaps our universe is not the first. Perhaps it will not be the last. And perhaps billions or even trillions of years from now, after the final stars have faded and the cosmos has completed its journey, everything we know will collapse, only to ignite another Big Bang. Another universe. Another beginning. 12. Could vacuum decay destroy everything? Imagine that everything you know, the Earth, the sun, the Milky Way, every atom in your body, and even the laws of physics themselves could disappear without warning. There would be no explosion to outrun, no alarm to sound, no chance to survive. The destruction would travel across the universe at the speed of light, silently rewriting reality itself. This chilling possibility is known as vacuum decay, and although it remains entirely hypothetical, it is rooted in some of the deepest ideas of modern quantum physics. To understand vacuum decay, we first need to rethink what physicists mean by the word vacuum. A vacuum is not simply empty space. According to quantum field theory, even the emptiest regions of the universe are filled with invisible quantum fields. These fields determine the masses of particles, the strengths of forces, and ultimately, the structure of reality itself. Now imagine a ball resting in a valley. At first glance, it appears stable. But if there is a deeper valley hidden nearby, the ball isn't in the lowest possible state. It occupies what physicists call a false vacuum, a temporary state that seems stable, but could eventually transition into a more stable one. Some physicists wonder whether our universe may exist in exactly such a state. If true, a random quantum event could someday trigger a transition to the true vacuum. The moment it happens, a tiny bubble of this lower energy state would appear. Then it would begin expanding, not slowly. Not at the speed of sound, not at the speed of light. Everything inside that expanding bubble would be transformed instantly. The fundamental constants of nature could change. Atoms might no longer hold together. Chemistry, stars, planets, and life itself could become impossible. Reality, as we know it, would simply cease to exist. The most unsettling part? No one would ever see it coming. Because nothing travels faster than light, the advancing boundary of the vacuum bubble would arrive at exactly the same moment its light reached you. There would be no warning, only immediate transformation. Fortunately, there is no evidence that vacuum decay has ever begun. In fact, calculations based on current measurements of particles, such as the Higgs boson, suggest that our universe is either completely stable or extraordinarily long-lived. Even if we occupy a false vacuum, theoretical estimates indicate that its lifetime could exceed the current age of the universe by an incomprehensibly large margin. Still, the question remains one of the most fascinating in theoretical physics. Is our universe resting peacefully at the lowest possible energy? Or are we balanced on a hidden ledge, protected only by the astonishing rarity of a quantum event? For now, the stars continue to shine. The atoms around us remain unchanged, and the laws of physics appear beautifully constant. Yet somewhere within the mathematics of quantum theory lies a reminder that the universe may not be as permanent as it seems. Reality itself could have another state waiting, one that, if ever reached, would redefine everything. 11. Are cosmic strings real? What if the universe still carries scars from its birth? Not galaxies, not black holes, but unimaginably thin cracks woven through the very fabric of space-time itself. These hypothetical objects are known as cosmic strings, and if they exist, they could be among the oldest structures in the universe, formed just fractions of a second after the Big Bang. To understand cosmic strings, imagine a lake freezing on a winter morning. As the ice forms, separate regions freeze independently. Where these regions meet, tiny cracks and imperfections can appear. These flaws are not created later. They are natural consequences of the freezing process itself. Some physicists believe the early universe may have behaved in a remarkably similar way. Immediately after the Big Bang, the universe was unimaginably hot. As it expanded and cooled, it passed through a series of phase transitions, much like water turning into ice. During these transitions, the fundamental fields governing the universe may not have settled perfectly everywhere at once. The result could have been incredibly narrow defects trapped within space itself. These are cosmic strings. Despite their name, they are not strings like those on a guitar, nor are they the tiny vibrating strings proposed in string theory. Instead, cosmic strings would be one-dimensional defects stretching across enormous distances, perhaps even spanning entire galaxies or crossing the observable universe. Their width would be microscopic, possibly smaller than an atomic nucleus. Yet their mass would be astonishing. A single kilometer of cosmic string could outweigh an entire mountain, or far more, depending on the model. Their immense energy would produce powerful gravitational effects, capable of bending light and influencing nearby matter. If a cosmic string passed between Earth and a distant galaxy, astronomers might observe an unusual form of gravitational lensing, creating duplicated images unlike those produced by ordinary galaxies or black holes. Scientists have searched for these signatures using some of the world's most powerful telescopes. They have also looked for ripples in space-time gravitational waves that might be produced if cosmic strings vibrate, collide, or snap. So far, no confirmed detection has been made, but the search continues. Finding even a single cosmic string would revolutionize physics. It would provide direct evidence of the extreme conditions that existed moments after the Big Bang and offer rare insight into the fundamental forces that shaped our universe. It could even help bridge the gap between particle physics and cosmology, bringing us closer to a unified understanding of nature. For now, cosmic strings remain theoretical, invisible, undetected, yet entirely possible. Somewhere across the vastness of the cosmos, ancient threads may still stretch through space, silent witnesses to the birth of everything we know. If they are out there, they are more than relics of the early universe. They are cosmic fossils preserved from the very first moments of time, waiting to reveal secrets that have remained hidden for nearly 14 billion years. 10. Why is there a huge cold spot in the cosmic microwave background? Imagine looking at the oldest light in the universe. A faint glow has filled the cosmos for nearly 13.8 billion years, a relic from the moment the universe first became transparent after the Big Bang. This ancient radiation, known as the cosmic microwave background, is remarkably uniform. Across billions of light years, its temperature varies by only tiny fractions of a degree. Yet hidden within this nearly perfect pattern lies one of cosmology's greatest puzzles. A vast region of the sky appears noticeably colder than expected. It is known simply as the cold spot. Discovered in maps of the cosmic microwave background, the cold spot spans nearly 1.8 billion light-years across if interpreted as a physical structure. Although the temperature difference is only about 70 microkelvin far smaller than anything we could ever feel, it is unusually large compared with the random fluctuations predicted by the standard model of cosmology. At first, scientists suspected a simple explanation. Perhaps the cold spot was merely a statistical coincidence, an exceptionally rare fluctuation that occasionally occurs in a random universe. After all, improbable events do happen. But as observations improved, researchers explored more intriguing possibilities. One idea involved an enormous supervoid, a gigantic region containing far fewer galaxies than average. As ancient microwave photons traveled through this underdense region, they could lose a small amount of energy because of the universe's accelerating expansion, making the area appear slightly colder. Astronomers searched for such a void and found evidence of a large underdense region in roughly the right direction. The problem? It doesn't seem large enough to explain the entire temperature anomaly. That opened the door to far more exotic ideas. Some cosmologists have proposed that the cold spot could be evidence of a collision between our universe and another universe during the earliest moments after the Big Bang. In certain models of eternal inflation, countless bubble universes may exist. If two of these bubbles briefly touched, the collision might have left a faint scar imprinted on the cosmic microwave background. It's a breathtaking possibility, a visible fingerprint from another universe. Yet extraordinary claims require extraordinary evidence. So far, no observation has confirmed this interpretation. Most scientists remain cautious, emphasizing that the cold spot may still be an unlikely but perfectly natural statistical fluctuation. The mystery persists because the cold spot sits at the boundary between ordinary probability and extraordinary physics. Every new observation sharpens the question. Is it simply a rare feature in an otherwise normal universe? Or is it the first clue that our cosmos is only one part of a far greater reality? For now, the oldest light in existence continues to whisper its secrets across the sky. Hidden within that ancient glow is a cold, silent region that refuses to fit neatly into our understanding. Perhaps it is merely a cosmic coincidence. Or perhaps, in that faint patch of darkness, the universe is pointing towards something unimaginably larger than itself. 9. What is the axis of evil? The universe is supposed to have no preferred direction. Whether you look north or south, east or west, the laws of physics should remain the same. On the largest scales, the cosmos is expected to be isotropic, appearing statistically identical in every direction. This assumption is one of the foundations of modern cosmology. But what if it isn't entirely true? More than 2 decades ago, scientists studying the cosmic microwave background, the oldest light in the universe, noticed something deeply unexpected. Several of the largest temperature patterns in the microwave sky appeared to line up along nearly the same direction. The alignment was so surprising that researchers jokingly gave it a dramatic name: the axis of evil. Despite the playful title, the mystery is taken seriously because it challenges one of cosmology's most fundamental assumptions. The cosmic microwave background is filled with tiny temperature variations, often described mathematically as different multipoles. According to the standard cosmological model, the orientations of these large-scale patterns should be random. Instead, the quadrupole and octopole, 2 of the largest structures in the microwave background, appear unusually aligned with one another. Even more puzzling, their alignment lies close to the plane of our solar system. Could this simply be a coincidence? Possibly. Random patterns occasionally produce surprising alignments, and some researchers argue that the statistical significance of the anomaly has been overstated. Others suggest a more mundane explanation. Perhaps the signal has been subtly contaminated by emissions from dust within our own galaxy, or by the complex process of removing foreground noise from the data. Tiny observational biases can sometimes create patterns that seem more meaningful than they really are. Yet the mystery refuses to disappear. Data from multiple space missions, including increasingly precise observations, have continued to reveal hints of the same unusual alignment. While the evidence remains inconclusive, it has encouraged scientists to consider far more adventurous possibilities. Some theories suggest that the universe may possess a subtle large-scale rotation. Others propose that space itself could have an unexpected geometric structure extending across billions of light years. A few even speculate that the anomaly might reflect unknown physics operating before or during cosmic inflation, the brief burst of expansion believed to have occurred just after the Big Bang. None of these ideas has been confirmed. The standard cosmological model continues to explain the overwhelming majority of observations with extraordinary accuracy. Yet the axis of evil serves as a reminder that even our best theories may still contain unanswered questions. Sometimes the universe whispers through tiny irregularities. A slight alignment, a faint pattern, a detail that refuses to vanish. Whether the axis of evil proves to be a statistical accident, an observational artifact, or the first glimpse of entirely new physics, one thing is certain: the oldest light in the universe still holds secrets. And somewhere within those ancient photons may lie the next great revolution in our understanding of the cosmos. 8. What causes fast radio bursts? Imagine receiving a message from the far edge of the universe. Not a sentence, not a signal carrying information. Just a single blinding flash of radio energy lasting less than the blink of an eye. In a few thousandths of a second, this mysterious burst can release as much energy as the sun emits over several days, and it vanishes. No warning. No explanation. These enigmatic events are known as fast radio bursts, or FRBs, and they have become one of the greatest unsolved mysteries in modern astronomy. The first fast radio burst was discovered in 2007, while astronomers were analyzing old telescope data. At first, many researchers suspected it was nothing more than interference from human technology. But as more bursts were detected from different parts of the sky, one astonishing fact became clear. These signals were arriving from far beyond our Milky Way. Some originated billions of light years away. Since then, astronomers have detected thousands of FRBs. Most appear only once, disappearing forever after a single flash. Others, however, repeat unpredictably, sometimes producing dozens or even hundreds of bursts over months or years. That difference has become one of the biggest clues. If some FRBs repeat, whatever creates them must survive the event. One leading explanation points to magnetars, young neutron stars with magnetic fields, trillions of times stronger than Earth's. When their magnetic fields suddenly rearrange or their crusts crack under enormous stress, they may release tremendous bursts of radio waves. In 2020, astronomers observed a magnetar in our own galaxy producing an FRB-like signal, providing the strongest evidence yet that at least some fast radio bursts originate this way. But magnetars may not explain everything. Some bursts are far more energetic than expected. Others display puzzling patterns, including intricate structures and unusual polarization that suggest they pass through extreme magnetic environments. This has inspired a wide range of ideas. Could some FRBs be produced by black holes interacting with dense plasma? By the collision of exotic stellar remnants? Or by physical processes we have not yet discovered? Of course, whenever mysterious signals arrive from space, speculation inevitably turns toward extraterrestrial intelligence. Could fast radio bursts be artificial transmissions? Most scientists think this is extremely unlikely. The immense energies involved would make such communication astonishingly inefficient, and every observation so far is consistent with natural astrophysical phenomena. Yet FRBs are more than cosmic curiosities. As these radio waves travel across billions of light years, they pass through clouds of gas scattered between galaxies. By studying how the signals change along the way, astronomers can use them as powerful probes to map the otherwise invisible matter filling the universe. In that sense, every mysterious flash is also a scientific tool. Each burst carries information from the deepest reaches of space. Each one is another clue. And somewhere among these fleeting whispers from distant galaxies may lie the key to understanding some of the most extreme environments the universe has ever created. 7. What accelerates ultra-high energy cosmic rays? Every second, invisible particles from outer space pass through your body. Most are harmless. Most carry relatively modest amounts of energy. But every so often, the universe sends something far more extraordinary. A single atomic particle slams into Earth's atmosphere, carrying more energy than a professionally thrown baseball, despite being smaller than an atom. How can nature produce something so unbelievably powerful? This is the mystery of ultra-high energy cosmic rays. Cosmic rays are charged particles, mostly protons and atomic nuclei, either travel through space at nearly the speed of light. They were discovered over a century ago, yet their most energetic members continue to defy explanation. The strongest of these particles, possess energies exceeding 100 quintillion electron volts. That is millions of times more energetic than anything humanity has ever created inside even our largest particle accelerators. When one of these particles strikes Earth's atmosphere, it collides with air molecules and unleashes a spectacular cascade of secondary particles. This enormous shower spreads across many square kilometers before reaching the ground. Observatories equipped with vast arrays of detectors wait patiently for these incredibly rare events. Sometimes they detect only a handful each year. The question is simple: where do they come from? One possibility points towards supermassive black holes lurking at the centers of active galaxies. As matter spirals inward, powerful magnetic fields and relativistic jets may accelerate particles to astonishing energies before ejecting them across intergalactic space. Another candidate is the aftermath of gamma-ray bursts, the most energetic explosions known in the universe. These cataclysmic events briefly outshine entire galaxies and may create shock waves capable of propelling particles to extreme speeds. Some scientists have also proposed rapidly spinning neutron stars, enormous galaxy clusters, or even exotic phenomena left over from the early universe. Yet identifying the true source is remarkably difficult. Unlike light, cosmic rays carry electric charge. As they travel through the tangled magnetic fields of galaxies and intergalactic space, their paths become twisted and distorted. By the time they reach Earth, they no longer point directly back to where they originated. It's as though every cosmic messenger arrives carrying its return address completely erased. Adding to the mystery is a theoretical limit known as the GZK cutoff. Particles with the highest energies should lose energy through interactions with the cosmic microwave background if they travel too far. This suggests that the most energetic cosmic rays must originate relatively nearby, within a few 100 million light years. And yet, no single class of nearby objects fully explains all of the observations. Every detected particle raises new questions. Some may have traveled across millions of light years before reaching our planet, carrying information from environments more violent than anything we can reproduce on Earth. These tiny messengers are among the fastest, most energetic travelers in the cosmos. They remind us that somewhere in the nearby universe, colossal natural accelerators are operating with a power far beyond our greatest machines. We have detected their products. We have measured their incredible energies. But the engines that launch them into the cosmos remain, for now, one of astronomy's greatest unsolved mysteries. 6. What is the Great Attractor? Every second, our galaxy is moving through space, not simply orbiting the center of the Milky Way, not merely drifting with the expansion of the universe. Our entire galaxy, along with the Andromeda Galaxy, thousands of neighboring galaxies, and the entire local group, is racing through the cosmos at more than 600 kilometers per second. But toward what? For decades, astronomers have traced this mysterious motion to an enormous gravitational influence known as the Great Attractor. It is one of the largest known structures affecting our corner of the universe, yet ironically, we cannot see most of it. The mystery begins with an unexpected observation. When scientists measure the expansion of the universe, galaxies generally move away from one another as space itself expands. But superimposed on that expansion are smaller motions caused by gravity. Our galaxy possesses one of these motions called a peculiar velocity that cannot be explained by nearby galaxies alone. Something enormous is pulling us. Following this invisible gravitational trail leads astronomers toward a region roughly 150 to 250 million light years away, hidden behind the dense stars, dust, and gas of our own Milky Way. This obscured area is known as the zone of avoidance because it blocks our view of distant galaxies. For years, the Great Attractor remained almost entirely hidden. As telescopes capable of observing infrared light, radio waves, and X-rays improved, scientists gradually uncovered vast clusters of galaxies lurking behind the Milky Way. These discoveries revealed that the Great Attractor is not a single gigantic object, but a sprawling concentration of galaxy clusters and dark matter, exerting tremendous gravitational influence. Yet even this wasn't the end of the story. Researchers later discovered an even larger structure beyond it, the Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe. Some evidence suggests that the Great Attractor and the Shapley supercluster work together, their combined gravity helping shape the motion of entire galaxy groups across hundreds of millions of light years. But gravity on this scale is astonishingly complex. Galaxies do not simply fall toward one object. Instead, they move within an intricate web of gravitational forces created by enormous clusters, invisible dark matter, and the expanding universe itself. Will the Milky Way eventually collide with the Great Attractor? Almost certainly not. The expansion of space and the vast distances involved mean that our galaxy's long-term future is far more complicated than a straightforward cosmic collision. Still, the Great Attractor reminds us that the visible universe is only part of the story. Much of its gravitational power comes from dark matter, an invisible substance that neither emits nor reflects light, yet outweighs ordinary matter by several times. Some of the greatest forces shaping our journey through space cannot be seen at all. Tonight, as you look up at the stars, remember this. Our entire galaxy is hurtling through the universe toward a destination we are only beginning to understand, pulled by invisible giants hidden beyond the Milky Way, across a cosmic landscape far larger than we ever imagined. 5. Why is there Hubble tension? How fast is the universe expanding? It sounds like a simple question. Measure the galaxies, do the math, find the answer. But one of the greatest crises in modern cosmology began when scientists did exactly that and obtained two different answers. Both measurements are extraordinarily precise. Both rely on decades of careful observation, and both appear to be correct. This mystery is known as Hubble tension, and it may be pointing toward new physics beyond our current understanding of the universe. The story begins with Edwin Hubble's groundbreaking discovery that distant galaxies are moving away from us. The farther a galaxy is, the faster it recedes, revealing that space itself is expanding. The rate of this expansion is called the Hubble constant. Determining its exact value has become one of astronomy's highest priorities. One approach measures relatively nearby galaxies using Cepheid variable stars and type Ea supernova as standard candles. Because astronomers know their intrinsic brightness, they can calculate distances and directly determine the present-day expansion rate. This method consistently finds a faster expanding universe. A second approach looks much farther back in time. By studying the cosmic microwave background, the faint afterglow of the Big Bang, scientists infer the expansion rate indirectly using the standard cosmological model. This method predicts a noticeably slower value for today's expansion. At first, researchers assumed the disagreement resulted from measurement errors. Perhaps one telescope required better calibration. Perhaps hidden systematic effects had been overlooked. But as observations became increasingly precise, the disagreement refused to disappear. Instead, it grew stronger. Today, the difference is large enough that many cosmologists believe it cannot be dismissed as mere statistical chance. So what could explain it? One possibility is that unknown observational biases still exist, affecting one or both measurement techniques in subtle ways. Another, far more exciting possibility is that the universe itself is revealing new physics. Perhaps dark energy evolves over time instead of remaining constant. Maybe an unknown type of elementary particle influenced the early universe. Some theories propose new interactions involving dark matter, while others suggest modifications to Einstein's theory of gravity on cosmic scales. Any of these possibilities would reshape our understanding of how the universe evolved. Or perhaps the answer is something entirely unexpected, something no one has yet imagined. The stakes could hardly be higher. If Hubble tension reflects genuine new physics, it would represent one of the most important discoveries since the confirmation of the expanding universe itself. Future observatories, more precise supernova surveys, improved galaxy maps, and next-generation space telescopes may finally reveal the source of the discrepancy. Until then, cosmologists are left with an extraordinary puzzle. The universe appears to be telling two different stories about its own expansion. Somewhere between those stories, a hidden piece of reality may still be waiting to be found. And solving that mystery could change our understanding of the cosmos forever. 4. Why haven't we found alien civilizations? Fermi Paradox. On a clear night, look up at the stars. Our galaxy alone contains hundreds of billions of them, many host planets. Across the observable universe, there are likely trillions upon trillions of worlds. The numbers are almost beyond imagination. So why does the universe seem so quiet? This simple question became one of the greatest mysteries in science after physicist Enrico Fermi famously asked, "Where is everybody?" Today, that question is known as the Fermi Paradox. Modern astronomy has transformed our understanding of the cosmos. Thousands of exoplanets have already been discovered, and many orbit within regions where liquid water could exist. If Earth is not unique, then life may have emerged countless times throughout cosmic history. Some of those worlds should have had billions of years, more than Earth, to evolve intelligent civilizations. Even traveling at a small fraction of the speed of light, a sufficiently advanced civilization could spread throughout the Milky Way in tens of millions of years. Brief moment compared with the galaxy's age of over 13 billion years. If intelligent life is common, if technology continues advancing, if civilizations survive long enough, then the galaxy should already be filled with evidence of their existence. Yet we see nothing. No confirmed spacecraft, no indisputable radio transmissions, no unmistakable signs of gigantic engineering projects surrounding distant stars. Just silence. Why? Perhaps intelligent life is extraordinarily rare. The leap from simple cells to complex animals may require such an improbable sequence of events that Earth is one of the few places where it ever happened. Or perhaps intelligent civilizations arise frequently, but rarely survive. Nuclear war, climate collapse, artificial intelligence, pandemics, or other self-inflicted disasters could end civilizations before they ever reach the stars. Some researchers suggest that advanced societies deliberately remain hidden, observing younger civilizations without interference, a concept often called the zoo hypothesis. Others argue that we simply haven't been listening long enough. Humanity has searched seriously for extraterrestrial signals for only a few decades, a tiny instant on the cosmic timescale. We may have examined only a microscopic fraction of the galaxy. It is also possible that alien civilizations communicate in ways we cannot yet recognize. Instead of radio waves, they might use technologies far beyond our current understanding, making their messages effectively invisible. Perhaps they are speaking, and we simply lack the ears to hear them. The Fermi Paradox has no confirmed answer. Instead, it forces us to confront profound questions about our place in the cosmos. Are we among countless intelligent civilizations, one of only a few? Or could humanity be the first technological species to emerge in our galaxy? Every new telescope brings us closer to discovering distant worlds. Every new mission expands the search. Somewhere among the stars, another civilization may already exist, waiting, wondering exactly the same thing, looking into the darkness and asking, "Where is everybody?" 3. What is the Great Filter? Imagine that every civilization in the universe begins the same journey. A lifeless planet. Simple chemistry. Primitive life. Intelligence. Technology. And eventually, the stars. It sounds inevitable. But what if almost no civilization ever completes that journey? What if somewhere along the path lies an obstacle so immense that nearly every species fails to overcome it? This unsettling possibility is known as the Great Filter. The idea was proposed as one possible solution to the Fermi Paradox, the mystery of why the universe appears so silent despite the enormous number of potentially habitable worlds. The Great Filter suggests that one or more stages in the evolution of intelligent life are extraordinarily unlikely. The crucial question is simple. Where is the filter? If it lies behind us, humanity may already have passed the hardest steps. Perhaps the origin of life itself is unimaginably rare. Maybe the transition from single-celled organisms to complex multicellular life almost never happens. On Earth, life appeared relatively early, but complex animals took billions of years to evolve. Intelligence capable of building technology emerged only very recently in cosmic history. If these evolutionary leaps are incredibly improbable, then intelligent civilizations may naturally be scarce. That would be good news. It would mean we are exceptionally fortunate. But there is another possibility. The filter may still lie ahead. Perhaps nearly every technological civilization eventually destroys itself. Nuclear conflict, runaway climate change, engineered pandemics, uncontrolled artificial intelligence. Resource exhaustion, or dangers we have not yet imagined. Civilizations may repeatedly reach a level of technological power that exceeds their wisdom, disappearing before they can establish lasting homes beyond their own planets. In that case, the silence of the galaxy would become a warning, not about the past, but about the future. Some scientists have even suggested that discovering simple life elsewhere in the universe could be deeply unsettling. If microbial life proves common, while advanced civilizations remain absent, it would imply that the truly difficult barrier comes later in evolution. Conversely, finding a galaxy already filled with thriving civilizations would suggest that the Great Filter, if it exists, is not insurmountable. At present, we simply do not know. The Great Filter remains a philosophical framework rather than a proven scientific theory. Yet, it has become one of the most thought-provoking ideas in discussions about humanity's long-term future. It asks us to think not only about alien civilizations, but about ourselves. Every scientific breakthrough, every environmental decision, every technological invention may help determine whether our species becomes another forgotten experiment in cosmic history, or one of the exceedingly rare civilizations that survives long enough to explore the stars. Somewhere ahead, a filter may exist. The greatest question is whether humanity has already passed it, or whether our true test is only just beginning. 2. What is the ultimate theory of everything? Imagine holding a single equation capable of explaining the entire universe. Every star, every atom. Every force of nature, every particle that has ever existed. One elegant framework describing reality from the smallest quantum fluctuations to the largest galaxy clusters. For more than a century, physicists have pursued this extraordinary dream. They call it the theory of everything. Despite the name, it is not a theory that answers every question. It would not explain love, consciousness, or the meaning of life. Instead, its goal is something equally profound: to unite all the fundamental laws governing the physical universe into one consistent description. Today, physics rests upon two astonishingly successful theories. The first is general relativity, Albert Einstein's masterpiece. It describes gravity as the curvature of space-time itself, predicting black holes, gravitational waves, and the expansion of the universe with remarkable accuracy. The second is quantum mechanics, which governs the bizarre behavior of particles at unimaginably small scales. Combined with the standard model of particle physics, it explains 3 of the 4 known fundamental forces and has passed every experimental test with extraordinary precision. Individually, these theories are triumphs. Together, they refuse to cooperate. Inside black holes, and during the first tiny fraction of a second after the Big Bang, both theories should apply simultaneously. Yet when physicists attempt to combine them, the mathematics breaks down. Infinity appears where meaningful answers should exist. Somewhere, something is missing. This has inspired generations of scientists to search for a deeper framework. One leading candidate is string theory, which proposes that the fundamental building blocks of nature are not point-like particles, but unimaginably tiny vibrating strings. Different vibrations give rise to different particles, much like different notes emerge from a violin string. Another approach, known as loop quantum gravity, suggests that space-time itself is woven from microscopic loops, making the fabric of the universe fundamentally discrete rather than perfectly smooth. Other ideas continue to emerge, each seeking to reconcile gravity with quantum mechanics. So far, however, no theory has been experimentally confirmed. The challenge is immense. The energies required to directly test many of these ideas are trillions of times greater than anything our most powerful particle accelerators can produce. Instead, physicists search for indirect clues hidden in gravitational waves, black holes, the cosmic microwave background, and the earliest moments of cosmic history. The search for a theory of everything is more than a quest for mathematical elegance. It is an attempt to discover whether the universe is ultimately built upon a single underlying principle, a hidden symmetry, a deeper reality from which every law of nature emerges. If such a theory exists, it could transform our understanding of space, time, matter, and the origin of the cosmos itself. Perhaps the countless equations filling modern physics are only fragments of a greater picture. And somewhere beyond them lies one simple idea, one beautiful equation, capable of explaining the universe in its entirety. 1. Why does anything exist at all? Every mystery in cosmology eventually leads to one final question. We ask what happened before the Big Bang. We ask how galaxies formed. We ask whether dark matter and dark energy shape the cosmos. But behind every discovery lies an even deeper mystery. Why is there anything at all? Why does a universe exist instead of absolute nothingness? It is the simplest question imaginable, and perhaps the most difficult question humanity has ever asked. For centuries, philosophers believed that nothing meant complete emptiness, the absence of matter, energy, space, and time. Modern physics has complicated that idea. According to quantum theory, what we call empty space is anything but empty. Even a perfect vacuum teems with fleeting quantum fluctuations, where particles briefly appear and vanish. The vacuum itself possesses energy, making nothing surprisingly active. But this only pushes the mystery one step further. Why do quantum fields exist? Why do the laws of physics exist? Why is there a vacuum capable of fluctuating in the first place? Some cosmologists have proposed that our universe could have emerged spontaneously from a quantum vacuum. In certain models, the total energy of the universe may even sum to zero, allowing a cosmos to arise without violating the known laws of physics. Others suggest that our universe is just one member of an enormous multiverse, where universes constantly form with different physical laws and constants. Still others believe that the laws of mathematics themselves make the universe inevitable, that reality exists because it must. Each idea offers remarkable possibilities, yet none fully answers the ultimate question, because every explanation seems to require something more fundamental, a law, a principle, a mathematical framework, or a deeper reality from which everything else emerges. Even time itself may not escape the mystery. If time began with the Big Bang, and asking what happened before may be meaningless. Without time, concepts such as before and after may simply not apply. Our intuition begins to fail. Language itself struggles to describe a state where neither space nor time exists. This is where cosmology meets philosophy. Science can describe how the universe evolved from its earliest measurable moments. It can explain the birth of stars, galaxies, black holes, and the elements that make life possible. But why there is a universe to evolve at all remains unanswered. Perhaps one day, a deeper theory will reveal that existence itself is inevitable. Perhaps the answer lies hidden within quantum gravity, the multiverse, or an entirely new understanding of reality. Or perhaps this question will forever remain beyond the reach of science. Every atom in your body, every galaxy across the observable universe, every thought you've ever had, every civilization that has ever lived, all of it exists because somehow reality chose existence over nothing, and until we understand why, the greatest mystery of the cosmos will not be what is out there among the stars. It will be why there are stars, why there is a universe, and why there is anything at all.